recording seems to work.
Resume recording. Okay, great.
Yeah, so guys, if you get over to the website, probably there is a chance that it could be done today after the talks. So you need it during the talks?
No, afterwards.
Yeah, you upload it also. Hopefully, after you can upload the recorded presentations thing. That's what we are planning. He's not the one who writes the earliest times. We're sort of I'd rather stay longer than starting at 8. I agree with you. Yes, CVPR 2022. Small. Lowercase. Hey, good morning, everyone. I think officially we should start, but let's wait 5 more minutes. I will check in the meantime if they hear us on Zoom and every other thing, but let's wait five more minutes so everybody can arrive who wants to arrive in five more minutes. Okay, so can you hear me on Zoom or see me or see the presentation, see the display?
Yes. Yeah.
Good, I heard a yes. That made me happy. Thank you. Okay, so we start in 5 minutes. Okay, the recording is on. Slideshow. Start from. You can still see the slides, right? Which do you see the presenter's view or the main one?
The presentation.
You see the presentation, not the presenter's view. That's good. Thank you. You see, guys, there's the reason why we wait 5 more minutes. There's a new person arriving in time, so we can look at him. You're welcome. Guys, do you mind if we present without mask? Who does? Raise your hands. Good. Sorry? Without mask. Yeah. But the cursor is visible, right? Do I see? Yeah, I see something moving there, so I guess it is. if you're actually considering using some laser pen, but that would probably not be the best for the people joining on Zoom. I mean, they wouldn't see. Okay, so actually the 5 minutes is gone. So good morning, everyone. Just for the people on Zoom to know that the room is actually full with thousands of people inside. They cannot get into the room. So good morning, everyone. I'm Daniel Bert, and I am the lucky one who will do this introduction today for the tutorial called Affine Correspondences and Their Applications. No, the button doesn't work, so let me, no. Now it works. So actually there will be 4 presenters today. Levente Haider will show you 2-view and multi-view problems. He is from Hungary, from Eötvös Loránd University. James Spritz will show you single view problems. He's from the Czech Technical University. Then Dimitri Mishkin will tell you how you can detect and match local features using affine correspondences and partially affine correspondences. He is also from the Czech Technical University and also from Hoover. And then in the end, I will show you how to use such features in practice. And I am Daniel Barrett and from ETH Zurich. Just to give you some intuition what we're going to talk about today, I want to show you with pictures what affine correspondences are. So basically, if we have a single image and we detect local features on it, so local features mean we have a point location, we can have other information regarding the region of which that point lies. And if we try writing down, describing the shape of the region by a 2 times 2, it's not an affine, but it's a linear transformation, then we get basically a local affine frame, and it is on 1 view. Then we have local affine frames in 2 views, and we do the matching procedure. So we find like point pairs, and we know the shape pairs too. Then we have a point correspondence, and we know the shape change as a 2 times 2 linear transformation in 2 images. This is called an affine correspondence, basically. Why we still call it as a affine correspondence, even though having only a linear transformation as a 2 times 2 matrix, because the translation basically is in the point locations. So this is how we get the translational part of the affine transformation, and the linear part is the shape basically of the region on which the feature lies. When having affine correspondences, we can do many things. So nowadays there are many algorithms for single view geometry problems, which Jimmy will show you. We can talk about vanishing point and line estimation. We can talk about scene plane segmentation, auto calibration, finding repetitive textures in an image. Then also we can talk about 2-view and multi-view problems. When having 2-view, of course, we can estimate homographies. We can estimate, so we can solve basically the most popular problems for 2-view and multi-view from affine correspondences. We have solvers for most of them. So like surface normal, multiplane segmentation, relative pose estimation, that includes fundamental matrix and essential matrix. Or we can have multi-view problems, for example, multi-view optimal surface normal estimation. We can estimate generalized pose for a camera rig. And also we can use affine features, and they really are used in detecting and matching local features. And Dimitri will show you how these things are done in practice. Some application. In the introduction, I wanted to show you mostly pictures and nice, colorful things, so you all start enjoying having affine correspondences. Of course, in the next slides, next presentations, they will often be dominated by equations. Sorry for that. But first, I wanted to show you some nice pictures. So basically what we can do from affine correspondences, we can go for reconstruction. We can go for visual localization too. So for example, in the left image, I hope my cursor is visible, right? I see it moving. So for example, in visual localization, we have a known map of the environment and we want to localize a new image or image, it went forward. And we want to localize a new image. And what we can do, in the map, we can easily calculate or easily estimate normals for each point. So we have an oriented point cloud in the map, for example, using the neighboring 3D points or something like that. And then using that normal and affine features in two images, in a query image and in a reference image, we can estimate the absolute pose of the image given a single affine correspondence. So this is usually the nice thing about you. I will show you some more motivation about this, but this is usually the nice thing about affine correspondences, that we need much fewer correspondences to estimate some geometric model than by using simply points. Of course, it has a dark side too. We will cover that slightly later. Also, we can do oriented point cloud reconstruction. So what happens in this case, we can detect affine correspondences in image pairs or tracks of affine features in multiple views. And then we can, for each correspondence independently, we can estimate a surface normal. And then here you can see this is one image from the sequence which is used. Again, these are the first images from the sequences. And then you can see the reconstructed point cloud. And these blue rods, I'm not sure how visible they are actually, but those are the estimated normals, point-wise, correspondence-wise normals, so there is no polishing on top of them. Also, this is another example on the right where we have some bone structure reconstructed, and again, we can go for oriented point cloud reconstruction. So we can use affine correspondences, for example, for this problem. Also, we can go for SLAM simultaneous localization and mapping. So we have solvers for generalized camera pose estimation in it. When we have a vehicle sensor camera system mounted to a moving vehicle, we can estimate the pose of the vehicle from actually two affine correspondences in contrast to the 6-point method, in contrast to the 6-point methods. Also, another colorful slide, so we can go for plane segmentation. We can do it even by detecting multiple homographies using affine correspondences. These actually, the images here are the first image of image pairs, and the top row is the segmented point cloud. So basically, color denotes the plane in these images. So we can go for multiple homography estimation and then do the segmentation and then do the reconstruction. And also we can go for oriented point cloud reconstruction and then do the segmentation using the point normals, basically. Another application, this is a single view problem. We can try finding image planes when we have repetitive texture in the image. So for example, the ground here is repetitive. And if you look around, here also in this room, the ground tends to have repetitive texture on it. Even we have tiles, now here the walls are also repetitive textures. So in man-made environment, such textures happen quite often. And we can use this information in order to, from a single image, get the plane. And this is the imaged vanishing line here in orange and here on in green. And these are detected from a single affine correspondence in an image, considering that we have repetitive texture. And this, when having the image plane found, we can actually do lots of things. For example, we can do gravity detection. So of course, if we know where the ground is, then we can estimate the gravity direction in the images. And if we do it image-wise, this helps a lot when doing, for example, relative pose estimation between images. So you know that when we have two images and we have the gravity direction for an IMU or, for example, by this method, then the relative pose estimation problem is much, much easier. We need only 3-point correspondences compared to the 5-point method. Also, when we have the image plane, when we have found image planes, we can use them in the next procedure to rectify the plane, basically. So we want, in this case, to transform the plane, the image, as if the plane is front to parallel to the camera, and we can use this. And for example, right image here is generated by using a single affine correspondence. So basically, in this case, we first found the image plane, and then in a hierarchical manner, we rectified the images to get these rectification. And this can help a lot in understanding the scene around us to reduce distortion, lens distortion, whatever we have in the images. So rectification is often used in practice too. Also, we can go for symmetry detection. This is again a single view problem. We can go for symmetry detection when having repetitive texture. So, for example, here is the input on the left. We can find different symmetric repetitive regions, and then we can use these regions to segment densely the pattern in the image. So for example, here you can see, I have no idea how this pattern is called, but it has a name, something. Or here, the poster wallpaper is segmented using this method with a single view here. So if I go back, you see the KitKats are not actually symmetrically placed, but still we can use this the constraint of having repetitive textures in order to segment them. And you can see that they are quite nicely defined, and the pixels are assigned to the objects. We can do other things. We can do auto calibration. So in this case, again, it is done from a single image. In this case, we assume a Manhattan frame. So basically, assuming that we have 3 orthogonal planes. This holds in many cases when we have buildings around us. And then we go from affine correspondences to vanishing point detection, and then from vanishing points we can estimate. We can auto-calibrate the cameras. We can get the rotation given that building. We can get the lens distortion parameters and all other kind of parameters which we want to estimate when trying to auto-calibrate an image. So this is another example. This is feature matching. Actually, people do not always realize that in feature matching, basically we cannot really do anything without having some, at least partially affine covariant features. Because what happens when doing feature detection and matching? We have 2 images. We do, not jump to the next slide. We use some feature detector, whatever, SIFT, for example. We use SIFT. Then the second step is we try to normalize the image patch around this the detected point, so they look like the same in the 2 images. And in order to do that, for example, when we have SIFT features, we have an orientation and we have a scale. We rotate the image patches so they are oriented the same in the 2 images, and then we set the sizes of the image feature of the patches so the size is also the same, and then it really helps in the matching, because then we extract some descriptors using, for example, the gradients and the image as done in SIFT. And then without this patch normalization, this description doesn't really work, or doesn't work as much as it can when doing this patch normalization. And of course, the more information we have, so if we have orientation and scale, that helps a lot. But if we have full affine frame, full affine feature there, that helps in reducing the projectivity in the image patches much more. What else we can do? So, for example, we can estimate dense features. There was a paper about it actually last year, it seems. where we can basically estimate local features for each pixel in the image. And then for each pixel, we do some dense nearest neighbor search to get a flow or so to get correspondences, which is then used for warping the images, to finding some transformation, some initial transformation between the images. So this is seen here. And then we can do some refinement to improve in an iterative manner the estimated transformation between the images. And these were the applications which I wanted to show you. Of course, I didn't show all of them. I just wanted to show a few of them, so you know that these affine correspondences are actually useful and not just sounds cool. But next, I want to discuss with you some benefits, some properties of these affine correspondences. And for example, the thing which we like and why we use affine correspondences is because they lead to some kind of covariance given the image transformation. So for example, here you can see the original image. This is the cat here, right? So we then detect some features that affine shape of the region, and that is the head of the cat basically. And we expect the affine covariant feature detector to find the same region, the same feature, the same region shape basically, after we warp the image by some affine transformation. So for example, here we warp the image, the cat, like this, and then we do apply again the same feature detector, and we expect to find to really figure out the shape of the transformed region. What we call repeatable and non-repeatable feature. So basically, there are two examples here. First one is, of course, the ground truth transformation of the feature, what we have. The second one is a repeatable feature. How we measure repeatability. Basically, it means that how much are we able to find to figure out the imaging transformation when detecting the features. So for example, it kind of measures, this is the Jacquard distance between the ellipses. That is the repeatability, but this basically measures the intersection of a union given the ellipses. And if it is kind of similar, then we call it repeatable. If the found feature is much different than what we want to find at that point, then we call it not repeatable. Why this is useful and how can we use this? So for example, if in this case we have again a single image, and we want to find a repeated pattern in the image, what can we do? We can do some affine covariant feature detection. We find features here. So these are the features, the points there. If we find the affine shape well, accurately enough, then we can use it to normalize the patches around the features like this. So for example, this T here are the green dots in the left image. And if we use the affine information, we can normalize them so they look the same in the cropped patches. Why it's good? Because then we do some clustering on top or whatever, and then we can find the repeated pattern. So basically, the patches which look the same in the same image will be the repeated pattern, and will be assigned to the same class, same label, or whatever we call it. So we want to be basically when talking about features. They will be covariant to the orientation scale and affine transformation. So this means that they will give us basically the orientation scale and affine transformation. But we want to use this covariance to make the image patches invariant to these transformations by normalizing them basically. So these are images from the H patches dataset, the whole image sequence. From left to right, there's a gradually increasing viewing angle given the image plane. What you can see here, basically there are ground truth transformations and there are detected transformations. The ground truth ones are the red ones. I'm not sure how visible they actually are. Not that important at this point. But what happened here? So basically we detected the features, we cut out the patches around and we normalized. And this is done here in the second row. So for each column here is a normalized feature in the same normalized feature in the 5 images. So for example, the first cell here belongs to one of the features in the first image. The second row belongs one of the features in the second image, etc. And the thing which you can see here, that the affine correspondences in the first rows are kind of good. What indicates this? These patches, these normalized patches, look very similar. Why it's good? Because then it's easy to match them, easy to find the pairs in the images, because we can use the affine information to reduce the effect coming from the viewpoint change, from whatever change we have. While in the second part of the bottom part of this figure, you can see again different features in the images, same image sequence. But the thing which you can see that it should not, and by the way, it should not be bad, but not repeatable, and the top should be repeatable, just to keep the terminology what we used before. And the thing which you can see here, that the columns are not too similar. The rows in the columns are not too similar, because they are, and this simulates like inaccurate, noisy affine transformations, which are not good enough to normalize the patches in a way that they can be found in multiple images. And you can see if you go from bottom to top, from top to bottom, that means from left to right in the sequence. And you can see that the bigger the viewpoint change is, so we are more to the right, the less likely that the normalized patch looks like as in the first row. Is it understandable? I'm not sure if I told it in an understandable way, but by the way, whenever you have any questions, something is not understandable, I want you to raise your hand and ask it again. I'm happy to tell everything twice, 3 times, even 4 times if needed. But I want you to understand the concepts. I want you to understand what really happens in this slides. So it's understandable, right? Good. Some examples of what kind of covariance we can have when having features. So of course, the minimal one is, I would say, the translational covariance, which means that actually we found the feature location in 2 images. That is what we have. That is the Harris detector, Hessian detector, superpoint. And here you can see this. So this is the original image in the top row. And being able to find the center, the same point, same feature point in 2 images means that we can cut out the window centered on for example, the middle of the eye. I should have put a point there in the middle of the eye, but I guess you can imagine a dot put there. So basically, this is a minimal thing which we want from a feature detector, being able to find feature points. Then what else can we have? We can have rotation covariant features and also scale covariant features. Usually they come together. For example, in SIFT, it is rotation and scale covariant. In ORB, it is kind of both, but people usually use just the orientation. But what happens if we have such additional covariances? Basically, we can use this rotation to rotate the image patches, so they are oriented the same in the 2 images. So this is this row here. We can use the scale to scale up the images to have the same size in the 2 images. And now you see that this eye became bigger, so it is as big as in the first image. Of course, there is still some effect, some projectivity there happening, but now the orientation and the size is good. Of course, then we can have affine covariant features, which will give us a full affine transformation here. We can have different ones. We can have handcrafted detectors, Hessian affine, MSCR. We can have learned detectors, for example, FNet. We can have simulation-based detectors, like using some view synthesis to warp the images by some artificial affine transformations and then find the features. There are lots of different kinds of approaches to find affine features. Most of them will be covered, hopefully, by Dimitro. So you will get to know more about this at that time. Also, we can have some region update based detector. So we have a region. There's a question, sorry.
Sorry. So to detect affine correspondences, which ones would be
True, it depends. And so Dimitro will tell exactly how to do the detection and which things are good. And in the last talk, I will tell which are the most accurate ones. So there is some drum in the background, and you will hear by the end of this tutorial what to use in practice and how to use them in practice. So I will answer this. Okay, can I ask one of you if there is some question? Just take the microphone there, maybe without the, I don't know. So you can go around like Freddie Mercury with the microphone on your shoulders. Okay, so let me continue. So the last row here is when we have affine correspondences. You can see that we can reduce the perfectivity as much as it's possible from affine correspondences, basically. Just quickly, so we don't have many slides left from the introduction, so don't worry, now the equations will come, don't worry. But how usually we represent affine transformations when it is drawn to images? So you might have seen images with circles, with oriented circles, whatever. So for example, even if I go back in the beginning of the presentation, you saw these with these oriented ellipses. And when representing affine features or rotation invariant features, etc., in images, we often use this representation. If I manage to go back, if we have rotation invariant feature, we use an oriented circle. If we have scale and orientation invariant feature, we use an ellipse. You can see that here the main axis coincide with the dominant axis of the ellipse. And when having affine correspondence, so basically the difference between having orientation and scale covariant correspondence features is that we have the shear parameter when having affine features. And that is usually drawn as oriented ellipses. You can see that in this case, the main axis do not coincide with the dominant axis of the ellipse. This is how we represent shear in images. But this is basically just how we draw on images, just so when you see a picture with affine correspondences on it, you will immediately know what you see by just knowing that this reasonably simple explanation. What are the main benefit when using affine correspondences? I think that is reasonably important. So as I told you in the beginning, when have affine correspondences, of course, have more information about the scene geometry than simply point correspondences. So don't just have a point location, it has some transformation between the image patches, basically. So it gives more information, more equations when estimating something. And this means in practice that we need fewer correspondences when estimating some geometric model, homography, relative pose, whatever we currently estimate. We need fewer correspondences than by using point correspondences. Why it's important? So basically, RANSAC-like robust estimators, probably all of you know what RANSAC is, but RANSAC-like robust estimators do minimal sampling, randomized minimal sampling, maybe with some guided sampler, but doesn't matter at this point. So they do randomized minimal sampling, where they select in each iteration, in the beginning of each iteration, minimal sample, which consists of m data points, where m is basically the number, how many samples, how many correspondences we need for the estimation. And the RANSAC iteration number, and thus the processing time, depends on that number, and it depends on it, not exponential, polynomially. So here an example in the table. Actually, this plot is the same as the table, but it looks like better that we have a plot there and also a table there. What you can see here, for example, when doing essential matrix estimation, we can estimate essential matrices from 5-point correspondences by the well-known 5-point algorithm. But actually, we can estimate essential matrices from 2 affine correspondences. And if you have a look on this table, so what you see, each column is an outlier ratio. And this is basically the adaptive RANSAC tabulation criterion output. If we have 95% outliers, it sometimes happens. Then when using affine correspondence-based solvers, we need to do around 2,000 iterations compared to the point-based solvers, where we need to do like 5 orders of magnitude more iterations. And this, of course, translates almost directly into the processing time, what we in theory should spend on that particular problem. Of course, usually we don't spend that many iterations, but in theory we should. This is one direct thing, one direct benefit from affine correspondences. But the thing is that RANSAC-like robust estimators, not just processing time-wise, but they really are sensitive to the complexity of the problem. What this means, if we have a very complex problem, we need to select 5, 7, 10, 20 point correspondences to estimate something, then the likelihood of really finding an accurate model is much smaller than when having a smaller sample size. So in RANSAC, it's really important in order to have accurate results to have as small sample as possible. Okay. I think this is the one before last slide. Just how we usually approach affine correspondences when doing something. The first thing which we can do, and that will be often done by Jimmy in his talk when having single view geometry, single view problems, we can convert affine correspondences to point correspondences. In two views, it is theoretically incorrect. In one view, we can do it. What happens in this case? So for example, we have these oriented ellipses, and now you know that oriented ellipse means affine correspondence. And we can basically introduce new correspondences where this main axis intersect the ellipse. So here we have this green correspondence. This is a new one. Here we have the blue correspondence. This is a new one again. And this orange correspondence is the center of the region. That is what we had earlier. So from one affine correspondence, we could generate 3-point correspondences and then use point-based methods to estimate whatever we want to estimate. Also, we can approach the problem, approach affine correspondences by defining them as a partial derivative of the imaging function. What is given the surface? In this case, basically, we assume that we observe a smooth surface with some surface normal on it, and the affine transformation is defined as the first order approximation of the imaging function if we move infinitely small steps in 3D along the tangent plane, basically at that point. It doesn't matter. Levente will tell you more about this in his talk. Also, we can approach affine correspondences via their effects on the epipolar geometry. So basically, when having affine correspondences, we assume that they will transform the normal of the epipolar line from the first image to the second one. So here we have this P point in the first image. We have this P1 and P2 in the second image. It is on some epipolar line when knowing the epipolar geometry, and we assume that the affine transformation transform the normal of the epipolar line to the from the first to the second image. So it rotates it, and also we have some scale constraint there. So this was kind of the introduction. Next, Levente will talk about stereo and multi-view problems. And then Dimitri Mishkin will talk about how to find the affine correspondences in practice, what to do with local feature, etc. Such nice things. Then we have a lunch break. Then Jimmy will talk about what to do when we have single images. We have one image. How to find repetitive structure, how to do vanishing point detection, how to do auto calibration, whatever we want to do. And then in the last presentation, I will show you basically two things. First one, how to use partially affine covariant features. What I mean, we have SIFT, we have orb, how to use the information which they provide, rotation and scale. And also I will show you the ways how can we really make affine correspondence-based robust estimation accurate. Under accurate, I mean more accurate than by using point correspondences, because it's quite tricky and it's not trivial how to do it, but it can be done. And this was my last slide. I think I forgot putting thank you for your attention and questions slide in it. But now, thank you for your attention. Questions? Thank you. So any questions? Yes? They are noisy. This is why you have to do lots of tricks to get a good result. The thing is, what happens? You have a point that is in the image coordinate system, basically. Then you try finding the transformation of the region. But the thing is that that's a local thing. So even a small noise can really have a big effect on the estimation. So even if you are almost perfect in terms of noise, that can be already too noisy when doing some estimation because of the local nature of such features. So you have to do things when using affine correspondences, like local optimization in RANSAC and such things in order to make them accurate. Can be done, but it's not real. Did I answer? I am not that sure about it. So tell me the question. Tell me the question. What didn't you understand? Yeah. Okay, and this is not the perfect answer. It's not trivial. It's easy. but not trivial. So you have to do what you have to know what to do to get accurate affine correspondence, accurate models from affine correspondences. Then it's implementation-wise, it's easy. People use locally optimized ransacs and such things, but that is really the core of getting them. Good. I answered. Okay. You don't look satisfied, and this is my problem. So, okay, but I won't satisfy you today. Okay. But sorry, tell. So you had.
What about the case of the cat?
Yeah, but in how many cases you find features on edges? I mean, a lot. So when you go for, of course, depends on the detector which you have. If you go for region-based detection, for example, you don't often find features in the edge. But the thing is that they are usually not that important. I mean, if you have, if you find a few good features, that usually is enough, and you need fewer than having point correspondences. So it's not a problem if you find just a few, I don't know, half of the features which you would find otherwise. But also you can go for, so if you don't go for affine features directly, you can go for SIFT features. And what happens when having SIFT features, people tend to simply forget about the orientation and the scale which SIFT features have when doing the model estimation. But see, you have the same number of features what you would use otherwise. You have SIFT features. You don't just use the point location, but also the orientation and the scale when estimating the features. And of course, around the edges, the orientation and scale won't be good, but anywhere else it will be good. And anyways, the last step is to refitting on the point coordinates usually. So it doesn't matter if the affine correspondence is inaccurate around the edges. Are you slightly happier? Good, I'm happy. Other questions? Okay, you can go ahead. Why not?
When you showed the picture, converting what you see is
it's amazing that I hear you verse through the microphone than when you talk without it.
Okay, I'll just go back.
Okay, no, go from there.
Sure. So when you showed the picture converting one you see to 3-point correspondence.
Yes.
Can they get as many points on this too?
The thing is that, of course, you can match. So the thing is that you don't have information about that. You can have additional procedure for matching along the feature, along the ellipse, but then that I wouldn't do. Then otherwise, instead, I would go for really matching features on the region silhouette, because that would make sense. On the ellipse, don't really. So you don't have information of which points correspond to which point on the other ellipses. You just only know that two dominant directions, basically. Yes. Ado, you had a question.
Are you going to kind of talk through the time when these affine features to sort of break down, because there's 3D structure and sometimes perspective change will cause, it's no longer a very good representation of a feature in the image plane.
Yeah.
We cover like how to kind of metrics for determining when that will fall apart.
Yes, of course, lots of things will be done. Of course, when doing affine correspondences, we explicitly assume a piecewise planar scene.
Sure.
But the thing is that in practice, what we usually do, you use this information only for the minimal sample models, for the hypothesis in ransack, and then you act as if you have no affine correspondences in many cases. So you have just the hypothesis, which comes from the fewer correspondences, and then you use only the point locations. So having this assumption that it's piecewise planar does not really matter anymore when doing ransack and such things.
So you rely on ransack.
Basically, yes, but as always, so you need some robust estimator by having real world data. You have to get rid of the outliers. You have to find out the model. It's just slightly more tricky when doing affine correspondences, but it is done, and it can be done easily. Other questions? I'm not sure what the time actually is, so let me check. Oh, we have 3 minutes for questions. That is amazing. That's lots of questions. Yes? Yeah? You mean we have 2 points and you want to upgrade them basically to have the share, the scale and everything, right? Or I think it usually comes from the feature detector, but there are of course methods upgrading affine features. But you know what happens, for example, in SIFT, you have the and also most of the orientation invariant features. Basically, you have the patch cutout, you have the image gradients, and then you do a voting to get the image feature orientation. You can do that anytime. The scale is more tricky. In SIFT, it comes from the scale space. But yeah, so it depends on the method you currently are using. Some things, for example, orientation can always be recovered independently of what features you have. And you can do tricks. And Dimitri will cover all these tricks and all these things in his talk.
Yes, I do.
Good. Other questions? I think we have time for one more question. Or two very short ones. Good. So if done, oh, there's a question.
What about the relational feature section? You have a couple of features there, and a couple of features in the other. Will we have that today?
I didn't hear half of the thing. I heard couple and features.
A couple of features in one image and a couple of features in the other, and they have a relation to each other.
Yes. In what sense? You mean you have correspondences?
Would it be better to incorporate the relation, the documentation of the couple into the correspondence analysis?
I am not sure if I understood the question. So
Well, you match one by one.
yes, or
Would it be better to match 3 by 3 or something like that?
the problem is maybe Dimitri is better to answer to the question, but the problem is when doing so you have points far away, then and even if they are not far away, so you have these are local features. If you go for 3 by 3, this means that you could estimate, for example, the affine transformation for these 3, and they are far away from each other. So the affine transformation will be a rough approximation of the actual one coming from the projective geometry. So if you define the affine correspondence as the first order approximation of the imaging function, this means that the affine correspondence at that point is true, is correct, only infinitely close to the features. Of course, few pixels are right, 10 pixels are right. But as soon as you go farther, then that approximation will be rougher and rougher, and then it won't really reflect the actual geometry behind the imaging procedure. Good. So thank you for your attention, and Levente comes to the stage. Shall I open Okay. My Mac knowledge is kind of lacking. This is yours?
Yes, it is.
And Dimitri, the Mac guru, is coming. So it needs 3 programmers to set up a presentation on a Mac.
So this one, so and you need the mesh lab.
Okay, I'm going back.
So mesh lab is here.
Okay.
This is here in house. Okay.
Thank you very much. I am sorry I haven't used Mac before, so, even if I'm quite old, so I'm not so young. So, I'm Levente Haider, and I am from Hungary, and I lead the group called Geometric Computer Vision Group, and maybe we use this name Geometric Computer Vision for our research because principally we don't build deep learning. We try to focus on geometric problems. And I started my PhD 20 years ago. And in that time, the Bible, the principal book was the book of Hartley's sermon. Please raise your hand if you know the multiple view geometry book. Okay, unfortunately, youngs don't know that. That was the Bible in that time. And in that book, the input for the algorithms were point correspondences. So there are images, there are several images, and then feature points are detected and matched between the images, and then several spatial entities are computed, like homographies or the point close, the 3-dimensional coordinates, or the fundamental matrix which represents the epipolar geometry between 2 views. The main message of my talk is that this point correspondence based geometric approach can be extended by the affine correspondences. So this tutorial deals with the utilization of affine correspondences for stereo reconstruction or stereo problems. And if I want to compress my talk then I want to state 3 different laws, and I will highlight these laws in my presentations, because 3 laws can be formed for the utilization of affine correspondences. And these laws will connect affine transformations, locations, and the images and in the space and camera parameters. You will see that a typical pipeline for PC means point correspondence based reconstruction which is overviewed in the book of Hart and Zisserman, and which is well known in the literature nowadays as well. So if somebody wants to do a 3D reconstruction, then first the camera is calibrated by usually a chessboard pattern, and then feature matching, feature matchers, and feature detectors and matchers are applied for the images. And then we have feature correspondences between the images. And then if we take 2 images, then the fundamental matrix can be estimated. If the cameras are calibrated, then the essential matrix can be computed from the fundamental matrix and the camera parameters. And finally, the 3D point cloud is computed by triangulation, via triangulation. And the result of such typical geometric algorithms are 3-dimensional point clouds. And in my talk, I will show you that this approach can be extended by the utilization of affine correspondences. And I will show you how homographies, fundamental and essential matrices, surface normals, and camera parameters can be computed by using affine correspondences. Let me overview in very brief the types of affine correspondences, even if Daniel overviewed it in one of his slides. Okay, in my presentation, I call the affine transformation principally this one, the linear part. So we have a point in the first image. I like to call it patch. Okay, it's not only a pixel, but a set of pixels around the locations. Okay, I call it patch, or I call them patches. And then we use a linear transformation for the coordinates, and then an offset is also added. Okay, so in total, an affine correspondence consists of 6 parameters, 4 parameters for the linear part, okay, this one, and then two coordinates for the translation. And in the linear part, different kind of transformations can be encoded. The translation is given by the AU and AV vector. Okay, this is the nonlinear part. This one, a rotation can be formed. I hope that you are familiar with this matrix. Okay, this is the standard rotation around the origin in 2D. If we scale the dimensions, the horizontal and vertical dimensions, then we can form the scaling transformation by this matrix, diagonal matrix. If the scaling parameters are less than 1, then the scale becomes smaller. Otherwise, if it's larger than 1, then that dimension becomes larger, and there is a different scale for the horizontal and the vertical directions. And the last parameter is the skew. It's also called the shear. And if we concatenate all these transformations, so in this example, skew and then scales are applied, and finally rotation, and then the offset is the last operation. Then if the input is a square here, then the resulting shape will be a parallelogram. Okay, so this is what can be obtained by an affine transformation, okay, by 6 parameters. But there are other decompositions. For example, if the linear part is decomposed into free matrices by the well-known singular value decomposition, in this case, free matrices are obtained, U and V, and the diagonal matrix in the middle. U and V are orthonormal matrices. So in two-dimensional case, they represent rotations, and the scales are inside in the middle matrix because it's the typical scale transformation. So in that case, the transformation can be decomposed. The linear part can be decomposed into rotation, then two scales, one along the horizontal and another one along the vertical dimension, and finally another rotation is applied. And if you use it, for example, for a circle, then an ellipse can be obtained, because the circle is rotated first, and then it's sheared and it's scaled, and then it becomes an ellipse, and then it's rotated by another angle. Okay, so this is the affine parameters in this talk, and I will show you how these 6 parameters can be utilized for several geometric problems. A very important property of an affine transformation, it's true for the linear part, then if we omit the translation, okay, in that case, this is the origin in the first image and the origin in the second one, it's in the middle of the shape. So the affine transformation, the linear part of the affine transformation preserves line directions. Okay, so if there is an affine transformation and we transform the lines, then the same affine transformation can be applied for all the lines which go through the origin. Okay, so the affine transformation transforms correctly the lines which go through the origin. Okay, this is a very important property. I remember a question after the introduction about the lines. So line directions can be applied to determine the affine transformation. This slide suggests that line directions can be used to estimate affine transformation. We will see it at close to the end of my presentation. Now let me overview the epipolar geometry. It's a standard epipolar geometry. Okay, so it's a stereo vision problem. In stereo vision, there are 2 images. Here is the first image, and here is the second one. We observe a small surface piece. Okay, I like to call it surflet. Okay, this surflet has a position, okay, denoted by x. Okay, it's a 3-dimensional position, so it can be represented by 3 parameters, x, y, z coordinates. And for the cameras, okay, they are now pinhole cameras, perspective cameras. So we have 2 focal points. C1 is the focal point for the first, and C2 is the focal point for the second parameter. And the projection is quite simple. We connect the spatial point x and the focal point C1 and C2. We get 2 projective lines. And that point is visible in the images in the pixel, which can be obtained as the intersection of the projecting ray and the image planes themselves. The geometry can be represented by the sorry, Dimitro, how can I hide this? Okay, maybe.
And move it somewhere. So
okay. Yeah, thank you. Okay, so this stereo problem can be represented by this so-called fundamental matrix. Okay, for the calibrated cameras, the camera parameters are encoded into an upper triangular matrix, which is the camera matrix. It's denoted by K1 and K2 in this talk. And if the cameras are calibrated, then the essential matrix can be formed by this formula. and the essential matrix encodes the pose, which is the translation and the rotation between the two images. If we fix the coordinate system for the first image, in that case, the horizontal and vertical directions give the first and second axis of the spatial coordinate system, and the third axis is the optical ray, and the rotation in the essential matrix, it can be retrieved from the essential matrix. It determines the rotation from the first camera to the second one, and the translation is given by a vector t. It's a translation vector. And unfortunately, if you know, you are familiar with stereogeometry, you know that the translation can only be reconstructed up to an unknown scale. Okay, so there is a scale ambiguity in the problem. This is why there are 5 parameters in the 3 parameters in the rotation matrix, and there is another 2 parameters in the translation, as the length of the translation vector is unknown. There is a well-known property for the fundamental matrix. If a P1 pixel location is given in the image space, in that case, an epipolar line can be computed in the second image. If the homogeneous coordinates of P1 is multiplied by F, and the first epipolar line can be computed if we multiply the P2 homogeneous coordinate in the second image by F transpose. Okay, they are well-known facts. And maybe I want to show you that the epipoles themselves can be computed. Epipoles are the intersections of the camera baseline. Camera baseline is the line which connects C1 and C2, the 2 camera focal points. And the epipole 1 is the intersection of the baseline, which is the first image plane, and E2 is the intersection with the second image plane. And there is a basic equation for the fundamental matrix. Okay, this one. So if the homogeneous coordinate of the second image point, it should be transposed, and it's multiplied by F, and then the first point comes, then that should be 0. Okay, it's a simple equation for the fundamental matrix, and it's a very important equation for no, because if only point correspondences are given, then for the fundamental matrix, we have one equation for each point correspondence. It's only one equation can be obtained. You will see that for affine correspondences, there are 2 other equations. Okay, and the last task in the epipolar geometry is the reconstruction when the spatial coordinate x should be obtained. So if P1 and P2, if everything is calibrated, which means that both the intrinsic parameters and the pose between the 2 images are given, in that case, P1 and P2 determines 2 projective rays, and we can determine these rays in the space. And if they intersect each other, then the spatial location is at the intersection. However, usually the projective rays are skew lines, so they don't intersect each other. So in that case, we have to find the closest point to the projective rays, computed projective rays. Okay, no, this is the introduction, and now let's move to the affine correspondences. And this is a motivation slide. Let's see this example. So this is a stereo problem, even if we have a camera and the camera is mounted on a car, and we take 2 photos at different times. And here you see that we are on the street, and there is a red lamp, and the other cars are waiting for the lamps. And now we highlight we select the different patches in the images. For example, here is the back size of this car, which is quite small in the first image, and it's significantly smaller in the second image because we go closer to the cars. And if you see these walls, for example, it's a wall of a building, and the size is approximately the same, a bit larger in the second image, but the difference is not as significant and the difference for the back size. And this example suggests that the scale itself, okay, which is a type of an affine transformation, the scale itself encodes some information about the depths. Okay, so if you can use the scale, then maybe we can improve the triangulation, contrary to the case when only the point correspondences are used. Because if the point correspondences are used, then maybe the middle point of the patch is selected here, and that determines two projective rays, and then the triangulation task is applied. Okay, but the affine correspondence, the affine transformation contains information about the depth. Okay, this is the main message of this slide. Okay, and here I put the overview of the literature of the utilization of affine correspondences, because not only for the triangulation, but for other tasks, the affine correspondences can be applied. And I'm not sure that I have found all the important publications in the field. That maybe the first publication is the paper of Megyesi et al. From 2006. It's an absolutely unhidden publication. It was published in a local Polish journal, as far as I remember. And in this paper, the images were rectified, and after the rectification, the affine transformations, the detection of affine transformation is easier. Because you know that the horizontal lines should be on the same line, the corresponding locations should be on the same line in the two images. And in that case, the affine transformation detection is an easier task. And they successfully computed the surface normal from this simplified affine transformation. Another very important work, and I think that this is the pioneering work in this field, is the PhD dissertation of Kevin Közer. He dealt with the estimation of the surface normals and camera pose, but only for also for a special stereo setup. And then other surface normals are estimators were published. Our paper is published in 2014 when we proposed an optimal surface normal estimator with Daniel Barat, and then we dealt with homography estimation. The first fundamental matrix estimation from affine correspondences was published in also 2014 by Bentolila and Francos. It's a journal paper. You remember that the fundamental matrix can be estimated from 7-point correspondences. They show that 3 affine correspondences are enough to estimate the fundamental matrix. The first 2 affine correspondence based estimator for the essential matrix was published in CVPR 2016 by Raposo and Barreto, 2 Portuguese researchers, and 1 year later, we proposed another one when the unknown focal length is also estimated, and then the special motions, the camera pose estimator for special motion was published later by us and by Goan et al. They utilized an IMU. So from an IMU, the gravity direction, the vertical direction can be obtained, and the gravity vector helps to simplify the problems. And they can estimate the camera pose from only a single affine correspondence. And the camera parameters can also be estimated for the other cases, and the complex non-stereo but multiple view problems can be also obtained by the utilization of affine transformations. So here are 2 papers on that topic. Let's move to the first law. Okay, and I want to highlight these 3 rows, because I think if you want to memorize something, then this is the task to remember that there are 3 laws for affine transformations. The first row, for the first row, let's take an object, a 3-dimensional object. Here it is, it's like a potato. And we take a quite planar surface. Okay, so a small surflet is represented here, and the 2 tangent directions are denoted by SU and SV in the space. If you are familiar with homography estimation, then you know that between a 3-dimensional planar object and the camera image, the homography determines the transformation. Okay, but the affine transformation is a simplified transformation because it only contains 6 parameters. But we need a center for to determine the offset between the 2 patches, okay, the patches in the surflet and the patches in the images, and the affine transformation transforms the neighboring area, the neighboring pixels around these centers. And József Molnár and Dimitri Csetverikov, they are also Hungarian researchers. Okay, Dimitri Csetverikov is originally Russian one, but he lives in Hungary. They were my colleagues at that time, and they showed that the affine transformation can be determined. So I know that at this moment you cannot understand why it is true. If you want to understand it, then please read the paper, read their paper. But they showed that the affine transformation between the 3-dimensional plane and the 2-dimensional image can be determined by the SU and SV. They are the tangent vectors, so they are 3-dimensional vectors. So this is, in the right, is a 3x2 matrix. Okay, and then it should be multiplied from the left by another matrix. It's a 2x3 matrix, which encodes the gradient. Okay, this is the gradient operator of the projective functions. So there is a projective function for the u coordinate. Okay, this is an image coordinate for the first coordinate in the image, which is denoted by pu. Okay, and the gradient means that the gradient with respect to the spatial coordinates. Okay, spatial coordinates x, y, z. So this is a free vector, row vector here for the first coordinate, projective function of the first coordinate, and there is another gradient for the second coordinate. The gradient is also with respect to the spatial coordinates x, y, z. Okay, so the affine transformation, because it's a local approximation of every kind of projection, it can be given by this formula. So by the multiplication of 2 matrices, a 2x3 containing the gradients and the 3x2 containing the surface tangent. And if we want to determine the affine transformation between the 2 images, then we should apply an inverse transformation. So we should move from the first image to the spatial plane, and then we should project it back again. Okay, and after geometric, differential geometric operations, the authors showed that the affine transformation can be written in this form. It's a quite ugly formula, but the message is quite simple. Okay, so here you see that the cross product matrix of the surface normal are in the middle. Okay, and then it should be multiplied by the gradient of the projective functions. Okay, there are 2 images, so there are projective functions for the first and the second images. The upper index denotes the image, and the lower index denotes whether it is the projective function for the u or the v coordinate is. And this is a complex but very useful. Very useful because it's a very general formula, so it doesn't depend on the applied camera model. So this is true for the perspective, for the pinhole cameras, but other camera models can also be applied. For example, omnidirectional cameras. Okay, the projective functions and the gradient of these projective functions differ, of course. So this is the first law. Okay, so there is I summarize it again. There is a formula for the affine transformation, and in this formula, the surface normal, the projective functions are used, the gradient of the projective functions, and these gradients the gradients encodes the spatial locations and the camera parameters, the applied camera parameters via the camera functions, projective functions. Okay, so this is the main message of this equation. Okay, and as affine transformations influences the spatial normal, the surface normal of these patches, So we can extend the standard point-based stereogeometry. So if we know not only the point locations between the images, but the affine transformations between the patches around the point locations, that patches determines the surface normal as well. Okay, and there is a formula which connects the surface normals, the spatial locations, the image locations, and the camera parameters. Okay, so this is the overview of the summary of the first law. Now let's see an example for the projective function. Okay, if we consider the well-known pinhole camera, this is the pinhole camera is represented by a 3x4 projective matrix. P11 is, for example, the element in the top left corner, and so on. In that case, this simple P11x plus P12y plus P13z plus P13 is the numerator for the first formula. It should be divided by the projective depth S, which can be obtained by this formula. So in that case, the third row of the projective function should be multiplied by in an inner product by the homogeneous coordinates of the spatial point. And if somebody take the gradients, then the gradients are quite simple. Okay, here you see that in the gradients, the projective parameters P11, P31, blah blah blah. I don't want to list all of them. Okay, the formula is quite simple. Okay, all the elements should be divided by the projective depths in these formulas. Okay, and this is the gradient for the pinhole cameras. For other types of cameras, like the omnidirectional cameras, the formulas will be more complex, of course. Okay, for the pinhole camera, it's quite easy. And as I mentioned before, in the middle of the 2010s, we proposed an optimal surface normal estimator, because the surface normal estimation problem can be, in the least square sense, can be formalized as this double sum. Okay, there are four parameters, four affine parameters, and the noise, the error for the affine parameters should be multiplied. And the formula is quite simple, because n transpose w's should be used where w's are calculated by the gradients. Okay, they are the cross products of different elements of the gradients. Okay, so the formula, mathematically, the formula is quite simple, and we prove that it can be optimally solved in the least square sense. And in that time, for the first publication, the roots of a quartic polynomial were required to obtain, but 2 years ago we proved that a cubic polynomial is enough. So there is a cubic polynomial. The roots of that cubic polynomials gives the optimal solution as well. And 1 year ago, I asked the mathematician to try to simplify this formula. And by a symbolic toolbox, he showed that linear formula exists to determine the optimal surface normal. Okay, and this is an unpublished result, so we will publish it soon. Okay, and now I hope that I can show you examples. Okay. No. Oh. I hope I can find a related 3D model. Sorry, I'm a bit lame. In this model, this is the model of my face. Oh, and I think that the length of the surface normal is too long. Okay, no, it's okay. So here you see Dima, can you help me? I cannot rotate it. What's happening? I don't know. It works before the presentation.
Yeah, what do you need? So what do you need?
I would like to rotate.
Like I never worked in Mesh Lab.
You don't know that. Okay, then I open it again. I think
yes. that's so here is your stuff.
That is the right click. Oh, I have a mouse, no problem. Okay, now I can rotate. So I try to find. Ah.
So what are you doing?
I don't know. I open it again.
Yes, so. Yeah, okay, so, okay, you're here.
Yes, but this is the back side. Then, yeah, okay, thank you.
Yeah.
I don't like Mac. It works very well in my Windows. It's freezed. So I'm sorry for that. Where is the presentation? Okay, so in this example, you would see my surface model, three-dimensional model, and the surface normals are also visualized. Okay, so believe me that it works. Yeah, I can show you in my laptop after the talk if you want to see it. Okay, so this is the first application. Because you see that there are numbers for the applications, so there are 3 laws, but many other applications will be overviewed in my presentation. Okay, I validated the result because I want to know what is the quality of the surface normals. So I constructed 3 different chessboards. It were fixed to a wood, and then the 3 planes were fixed by screws. So 3 perpendicular chessboard patterns are used to the validation. And in the chessboards, not only the point locations, but from the directions, the affine correspondences can also be determined. And I did a 3-dimensional reconstruction, and then I could quantitatively compare the quality of the surface normals. And as far as I remember, the angular error was below 2 degrees. Okay, so this example suggests that it is possible to retrieve the affine transformations from the images, and the quality of the affine transformations are enough to obtain good reconstruction for the surface normals. And the second applications, you saw the law for the formula for the affine transformation. If the surface normals and the spatial locations are known, then the camera parameters can also be computed. So in this example, we use a cube for the size, the surface normals are known because they are perpendicular to each other. And then the camera we successfully retrieve the camera parameters from this example. And as in the gradients, the spatial locations are also applied, so we can compute the spatial coordinates from the affine transformation. But I want to tell you that this is an open problem because we have, so theoretically it's true, but we haven't implemented an accurate triangulator which utilizes the affine transformations. So it's an open problem. We would be happy if other researchers would deal with this problem and solve the triangulation, for example. Okay, and the next note about this formula. So maybe you know the Bendel adjustment algorithm. So it's an outlook to the multiple view problem. So if we have many other images, the benefit of affine transformations are that an affine transformation can be determined between only 2 images, and the other images don't influence the affine transformations. So if we take the Bendel adjustment algorithm, then it can be extended. So not only the point locations, the 2-dimensional locations, but the affine transformation can be given for Bendel adjustment as an input. And in that case, the output is not only 3-dimensional coordinates, but surface normals. So surface normals can also be involved into this problem. Okay, we have implemented a simplified solution for this problem. In that case, the surface the surflet itself was represented by an affine frame. So in that case, not the original program was old, but was solved. But as the problem is very sparse, here is the normal equation for the standard bundle adjustment. Okay, in this sample, for the surflet, not only a three-dimensional location, 3 coordinates, but 2 normal parameters should be added. So in that case, there are 5 parameters for each surflet points, and the camera parameters are the same. But if we involve the affine parameters into the problem, then the relationship, the derivatives with respect to the camera parameters becomes more complex, because in the standard point correspondence-based bundle adjustment, one spatial locations depends only on the image coordinates. Sorry, one image coordinates only depends on the corresponding spatial coordinate and the corresponding camera parameters, but affine transformation depends on 2 camera parameters, okay, the 2 parameters of 2 cameras, not only one. So in that case, this part of the normal equation should be modified, but I hope that it can also be solved. But it's also an open problem, so it hasn't been solved correctly yet. Now let's move to the second law. This is the simplest law, I think, because the affine transformation is the local approximation of every kind of projection between 2 images which project the surface patches. Now let's consider the homography itself. We know that if we have a planar objects, which is the chessboard in this example, then the homography can transform the edges of the borders of this chessboards correctly to the second image. But if we use the affine transformation, in that case, it's only locally a good approximation. So we select this bottom left corner here and here, and the affine, if we determine the affine transformation between these corners, okay, and the local neighborhooding pixels, in that case, the top right part was incorrectly transformed, of course, but see that the images, okay, the edges along these 2 lines are correct. So this shows that the affine transformation transforms the edges around the origin, okay, the lines around the origin correctly. Okay, but all other lines, the lines at other locations are incorrectly transformed, of course. The equation for the second law, here they are equations. There are 4 equations, and if somebody take the partial derivatives, as the affine transformation is a local approximation, the linear part can be determined by the partial derivative of the second coordinates with respect to the first one. A11 is the partial derivative of u2 with respect to u1. The A12 is u2 with respect to v1, and A11 is partial v2 partial u1, and A22 is partial v2 partial v1. Okay, so the formulas are quite simple, and if somebody computes the derivatives, then this formula is obtained. Okay, and we will use this formula. Okay, let's focus on these formulas. So we have an equation, 4 equations, sorry, for the affine parameters, and these equations contains image coordinates, the point locations, and the homography parameters. Okay, there are only 5. Homography is a 3x3 matrix, so there are 9 parameters, but we know the scale is not important, so the degrees of freedom are 8 in this case. So we have 4 equations in order to compute 8 degrees of freedom. A problem is that so in the last column, or the first and second element, age 1 free and age 2 free are not involved into these equations. Okay, so these elements can be computed from the point locations only, but the other parameters can be estimated from the affine transformations. Okay, and now let's count the equations. So for homography from the point locations, we have two equations. Okay, it's the standard problem. And from the affine parameters, we have additional 4 parameters. So we have 6 parameters in total if we want to estimate the homography itself. Okay, and as the degrees of freedom 8, then only 2 affine correspondences are required in order to estimate the homography. So this is why 2 affine correspondence-based homography estimator is possible. Okay, and if only point correspondences are used, then at least 4 point correspondences should be taken. This is the minimal case for obtaining a homography. Okay, so the problem can be computed from less correspondences, and Daniel showed different tables for the time demand of Ransec, for example. So for our robustification, it's very important to retrieve the model from as minimal correspondences as possible. A special case then when the fundamental matrix, the epipolar geometry is known between the 2 images. In that case, at least 3 point correspondences are required for the standard problem. But if affine correspondences can be used, then only a single 1 affine correspondence is enough to obtain the homography. Okay, so from only 1 local information, the homography can be retrieved. So a trivial application of the second law is the homography estimation. We know that only 2 affine correspondences are required for the general case, and if the fundamental matrix is known, then only a single affine correspondence should be taken to compute the homography. And another trivial problem is the multi-model fitting, multiple plane fitting. Daniel is a master in multimodal fitting, and the plane segmentation, as the plane segmentation can be obtained from 1 correspondence if the epipolar geometry is known. So the multiple plane segmentation is a less challenging problem than for the general case. Okay, and we could solve this problem, and we get nice results for multiple plane fitting. Now let's move to the last law. This is the third law for this utilization of affine correspondence. Here in this law, we wanted to connect the fundamental matrix and the affine correspondence. It's interesting that this work was motivated by Jiří Matas, the famous Czech researcher, because we met in a conference and then we presented him the theory for affine correspondences, and then he asked whether because he remembered that for point correspondences, if the stereo problem is the stereo geometry is known, then we can correct the point correspondences in order to fulfill the epipolar geometry. So in that case, the corresponding points should be on the same epipolar lines. And he asked me whether it can be some constraint can be written for the affine transformation as well if the fundamental matrix is known. Okay, and we did the following proof. So following process, we take 1 point in the first image here, P1, and we take this corresponding point in the second image. Okay, they are given by the point correspondences, so nothing special I did at this moment. And then we move from P1 along the normal direction of the epipolar line. Okay, here L1 is the epipolar line for the first point, and L2 is the second point. And we move to another point, Q1, and we take the epipolar line for that Q1, and then we compute the corresponding epipolar line, L'2 in the second image. And then we determine the distance of P2 and the epipolar line L'2. Okay, this is a point line directions. And if this epsilon, okay, the distance between Q1 and P1 is very small, infinitely small, in that case, this direction vector represented by D is perpendicular to L2 as well. And the difference, the ratio of D, the difference in the second image, and epsilon gives the scale along the normal of the vertical line. Okay, and we could prove that there is a formula for the fundamental matrix and the affine transformation. Okay, in this one, P1, P2 are the two-dimensional point coordinates. The homogeneous form should be used. And there are hat and tilde F here. Hat and tilde F comes from the fundamental matrix. The last row and the last column should be cut. Okay, so these are 3 by 2 and 2 by 3 matrices. So there is a formula here, and you see that the transpose of the affine transformations are written, in the left. I cannot highlight it. Okay, so there is a formula which connects the affine transformation, the fundamental matrix, and the point locations. Okay, and this seems to be one equation, but it's a two-dimensional formula. So there are two equations which connects affine transformations, fundamental matrix, and the point locations. Okay, and this is the message of the third law, that there is a formula which connects pixel coordinates, fundamental matrix parameters, and the affine transformations. Last remark that as the last row and the last column from the fundamental matrix are cut, so the bottom right element is not considered in this formula. Okay, so that element can only be estimated from point correspondences, from at least one point correspondence, that all the other elements can be estimated from the linear part of the affine transformations. Okay, but it's not a problem, because if I say that we use the affine correspondence, then the linear part and the offset are also considered. So the offset comes from the point correspondence. Okay, so this is the last message. A remark that if we multiply P1, the homogeneous form of the first coordinate with the fundamental matrix, then a line is given, and the first two coordinates are the normal of the epipolar lines. So this formula connects the normal directions along the epipolar lines in the second image and in the third one. And there is a scale between those, which is denoted by beta, but this beta can be computed. Okay, so it's a known value. So we have two equations that connects affine transformation and the fundamental matrix and the point locations. So a straightforward application of this theory is that if we have affine correspondences, then we want to compute the fundamental matrix. For the general fundamental matrix, degrees of freedom are 7. So we have one equation for the point correspondence, additional two for the affine parameters. So we have 3 equations from one affine correspondence. So we have 3 affine correspondence to compute the general fundamental matrix. But if the cameras are calibrated and the essential matrix should be computed, in that case, only 2 affine correspondences are required for the operation. A special case when the motion is planar, for example, when we have a camera mounted on a vehicle and the road is planar. So in that case, the movement between 2 frames can be given by a translation parameter and a rotation parameter, but the scale of the translation is unknown. Okay, it's a 2-dimensional translation. So in that case, we have only one rotation parameter and one translation parameter, and we have 3 equations. So for the planar motion, the fundamental matrix of the camera pose can be estimated only from a single correspondence, and we have 3 equations for 2 unknowns. So we have one freedom, and for example, if the cameras are semi-calibrated, which means that the same focal lengths are the same for all the images, but the focal length itself is unknown. In that case, the focal length can also be obtained, or which is written in the CVPR paper of Guan et al. If there is an IMU and the gravity direction can be retrieved from the data, then only a single affine correspondence is required. And I think that it's a very important result, because if only point correspondences are required, then we need 2 points, okay, two corresponding points in the 2 images. And for numerical stability, it's better if the 2 points are far from each other. But if we use one affine correspondence, then the camera pose can be retrieved from local data. Okay, so not global data to not close point correspondences, but one local affine correspondence can give the camera pose. It can give enough information in order to compute the camera pose. Okay, so this is why, for example, affine correspondence can be used for the visual odometry problem. And I asked Dima to start the video because I think that I am not able to start it.
Okay.
There's a folder odometry.
And what is this folder odometry?
And Malaga, the last one. Here you see an image sequence from the Malaga dataset. We take several images, and the pose between two images are determined by the proposed affine correspondence-based algorithm, and robustification should also be considered in this task, and not a ransack, but a histogram voting is applied here. For the rotation, as far as I remember, this video was computed, I think 3 or 4 years ago, and you see that at this moment the car takes a turn, and in the next part you see that the sun is in front of the car, and the quality, the contrast of the image here, the video here becomes very low. But the algorithm can cope with this is quite a challenging situation as well. Yeah. Yes.
So how sensitive is this visual odometry? So in turns, for example.
Yeah. Loop closure is not applied, and there is significant risk between those. Okay, but in that case, we only want to focus on whether it is possible to retrieve the camera pose from an affine correspondence. So the SLAM problem is not deeply considered. Oh, there is the presentation. Which one is the full screen mode? The green one?
Yes, green one.
Okay, here you see the 6th application, which is the visual odometry. I mentioned you that this task was motivated by the correction of the affine frame. So Izsi Matas asked us whether the affine transformation can be corrected if the epipolar geometry is known. Here you see how the point correspondences can be corrected. Here is the original problem. We have 2 points, the first and in the second image. The corresponding lines are denoted by black here in the first image and black in the second image. For the second point, the corresponding lines are visualized by red. And you see that unfortunately the 2 lines are not the same. So the problem is, mathematically, the problem is that we want to find and this is the idea from Professor Hartley and Peter Sturm. This algorithm is called Hartley-Sturm triangulation. They proposed an algorithm. They want to find corresponding epipolar lines, but the closest epipolar line. So distance with respect to the original point and the epipolar lines should be minimal. And the Euclidean distance, could be solved, this problem for the Euclidean, for minimizing the Euclidean distance. And as far as I remember, the roots of a 5th order polynomial should be computed in order to determine this task, and then the point locations can be corrected. Okay, and now let's see the solution for the affine transformation. We have constraint for the surface normals. The two equations are encoded into this single formula. So for the normal of the epipolar lines, for a consistent, if the affine transformation is consistent with the epipolar geometry, then this formula is true. Okay, so we have two equations. This is only the linear part of the affine transformation is involved. So we have four free parameters in the affine transformations, and we have two constraints, two equations. And if the Lagrangian multiplier technique is used, in that case, we should include two Lagrangian parameters, and we have more equations. And finally, a six-dimensional but linear equation was formed. Okay, the six-dimensional comes from the four affine parameters, four linear parameters, and the two Lagrangian multipliers. And as the program is linear, then it suggests that a matrix inversion should be applied. So there is a closed form formula in order to determine the correction of the affine parameters, and at the end, the consistent affine transformation is obtained. Another possibility, it's also an open question, so I wanted to highlight here, I wanted to overview here a possible reconstruction pipeline for the affine frames. When the chessboard example was showed, so when I constructed three perpendicular chessboards, in that case, this pipeline or the simplification of this pipeline was applied for the process. So we have input images. This is the input for the extended pipeline, and the output is an oriented point cloud. Oriented point cloud means a point cloud with surface with normals. So each three-dimensional point has the normal direction as well. So we know the tangent plane at that locations. And maybe the first task is to estimate the fundamental matrix. So we take two images, estimate the fundamental matrix from point correspondences. Then a raw fundamental matrix is obtained. In that case, we can compute affine parameters, because the fundamental matrix can be the knowledge of the fundamental matrix can be involved into the affine estimation problem, and then we can improve the fundamental matrix, and we have a improved one. Then the standard triangulation is applied without affine transformation. But I mentioned you that the triangulation from affine correspondences is also an open problem. So the triangulation can also be used, but in this pipeline only point correspondences are used. So the standard triangulation, for example, the triangulation of Hartley and Sturm are applied. And then we have the spatial locations, and we add the spatial locations and the affine transformations into a new block, which is the estimation of the surface normals. Here they can be estimated, as I showed before, the surface normals can be optimally estimated in the least square sense. And then all the point clouds, the surface normals, and the camera parameters, and the other stereo, the results of other stereo reconstructions can be feeded into a Bentley adjustment step, and then this Bentley adjustment can retrieve from the oriented point cloud, and the camera parameters are also computed, of course. Okay, so this is a possible extension of the standard point cloud based reconstruction to utilize to exploit the affine correspondences. And also a possible application is a perspective structure from motion using affine correspondences. I show you my face, three-dimensional model of my face. That algorithm was computed by our multi-view extension algorithm, so that results weren't obtained by stereo images. In that case, multiple view images are used. Okay, and finally, a few remarks about the estimation of affine correspondences, because I think that this is the dark side of this theory, that for good reconstruction, good affine correspondences are used. And my colleagues deal with this problem. You will see the presentation here, how affine correspondences can be retrieved. But I would like to show you another possibility, which is also an open question. For me, the feature detection and tracking are black boxes. So I usually use them and as a black box or a run and then retrieve the data, and then I apply the result. Daniel implemented me several affine correspondence matcher, and his idea was to similar to the SIFT algorithm. I don't know you are familiar with SIFT. That SIFT is well known. Affine SIFT is a modification when we take the images and one of the images are transformed by different affine transformations, and the SIFT algorithm is applied for the transform version. And in that case, if the matcher finds a matching, then that affine transformation is applied as the output, okay, as the corresponding affine transformation. And this idea can be used for several feature detectors and matchers. Here you see a list, but I don't want to tell too much about them because I am not familiar with this topic. But there is another technique, which is also an open question, because in this first part of my presentation, I told you that one important property that the affine transformations transform the lines correctly, which go through the origin. And if we have such directions in the first and the second images, then the affine transformation connects those. So if we have L1 aligned direction in the first image, and in this case it should be the length should be unit. Then in the second image, we have another direction, and if we match lines in the two images, then we can determine these directions. But unfortunately, the scale which is denoted by alpha, is unknown. Okay, so if we use line matchers, then we have equations, two equations. Okay, this formula is a two-dimensional equation, so it consists of two equations. But if the scales are unknown, then the scale alpha is also unknown. So we have two equations, but another alpha is involved into the problem. Theoretically, as there are four affine parameters, then we need four equations. As one equation reduces the degrees of freedom by only one. But if the scales are not known, in that case, an equation contains two degrees. So an equation can reduce 2 degrees. And recall that the fundamental matrix itself, if the fundamental matrix is known, in that case, for the surface normal, we have an equation, two equations, formula which is a two-dimensional formula, and in that case the scale is known. Okay, so that the fundamental matrix itself can reduce the degrees of freedom by 2, and in that case we need the fundamental matrix and one scaled direction, or we need the fundamental matrix and two unscaled directions, or we need several unscaled directions, but it should be noted, but the scale is very important because the scale parameter cannot be retrieved if only directions are known, but the scale itself is not. So at least one scale direction or the fundamental matrices are required. Okay, and this concludes my talk. So I hope that I can show you that this is a very interesting new research field. There are many papers in the last 10 years which has dealt with this problem. Several algorithms proposed, several solvers proposed in order to obtain geometric entities like homographies, fundamental matrices, spatial coordinate, surface normals. But the main message of my talk would like to be 3 statements. The first law is that there is a relationship between surface normal, affine transformations, projective functions. Oh, and then the spatial location is missing here. So spatial location is also required. So there is a formula which connects camera parameters, spatial location, surface normals, and image coordinates plus affine parameters. There is a formula which consists of 4 equations for the homography estimation. So if an affine correspondence is known, from the linear part, we have 4 additional equations in order to estimate the homography, and point locations gives additionally 2 parameters. So from an affine, oh, sorry. I think I enable it. Okay, so from an affine correspondence, there are 6 equations, and for pinhole cameras, an affine transformation gives 2 constraints for the epipolar geometry. And here, novel estimators has been introduced for solving the surface normal estimation problem. Camera intrinsic, extrinsic parameters can be estimated. Fundamental or essential matrices can be estimated. There are special cases like the camera pose for planar motion, or when the gravity direction is known from an IMU. And what's happening? We overviewed several applications. I showed you results from surface normal estimation, camera parameter calibration, Bentley adjustment algorithm was also considered here. Homography estimation for plane fitting was applied. Homography estimation was applied for multiple plane fitting as well. And I show you an example for the visual odometry. I want to encourage all the participants to deal with this problem, because there are open problems in the field, like the triangulation, the optimal camera calibration. The general Bentley adjustment algorithm hasn't been proposed yet, and I think that there are other open questions as well. So this is all. Thank you for your attention. Dima.
I have 2 questions. One is, so I understand it's topic about stereo, but is there a formulation for PNP using affine correspondences?
For PMP?
Yeah.
Oh. That's also an open question. I don't know. I don't.
There is. That's one of the.
Hmm?
And second, when would we have affine coma?
Affine what?
Coma. So like there is coma who everybody uses. It's like tool for 3D construction.
Yes.
What you would incorporate?
I think we would like to incorporate in Colmap, because unfortunately I haven't used Colmap. Okay, this is my weakness, but I've seen several results from Colmap, and I think that it's a straightforward task to extend this tool with affine correspondence. So that's a good idea. Thank you for that. Other questions or remarks? Yes.
So for estimating that.
Yeah. Yes.
Couldn't you also use 2D?
Yeah. Yes, you're absolutely right. So if you have 2 affine correspondences, then you have 6 equations, and the remaining 1 can be retrieved from a single point correspondence. Yes, that's a viable solution for this problem. Okay, maybe there are degeneracies, of course, but that should be handled one by one.
Because it seems like this would be the actual minimal way to solve.
Sorry?
It seems like this would be the actual minimal way to solve.
Yes, you are right. Thank you for this remark. Oh, and how can I listen it?
Could you please repeat questions for the stream? Okay, that's a good point. So when someone asks questions or repeat it.
Yes, that's also a good advice. Yes, please. Please use the microphone. Okay.
So for the surface normal, you show that you only need one issue, like a curve of
Yes, only one.
You showed an example of dense surface normal. So I was wondering how many AC pairs did you get for the full constructions? And it's a way to find like a affine field or something small in the image domains of consider like a geometrical flow, like a field to be motion, but with affine motion. There are not so I was wondering how many pairs did you use?
Yes, you are absolutely right that for each surface normal, an affine transformation is required. So if we would like to compute, sorry, if we would like to compute 10,000 oriented point clouds, then in that case we need 10,000 affine correspondences. And we tried optical flow in order to retrieve affine transformations, but we were not satisfied with the quality of the I remember for that problem. So we usually the image of a vehicle mounted camera, okay, to do a feature matching, not feature matching, but in that case, we know the flow between two images, and then we can compute the movement between the image locations, the corresponding points, and the affine transformations can also be estimated from the neighboring, for the movement, for the flow of the neighboring points. But the quality was the quality of the resulting oriented point clouds wasn't so good, so we were not satisfied with the results. Okay, but I think that the affine correspondence estimation, so how good affine parameters can be retrieved from images, it's a very important question, because the quality of the reconstruction highly depends on the quality of the affine transformations. Okay, this is why I constructed that three perpendicular chessboard calibration objects, because I wanted to verify, I wanted to validate that from noisy data the surface normals can be accurately retrieved. Okay, and I think this is the case, but improvements are required for the affine parameter as affine matchers. Okay. Are there any other questions? Okay. Yes. Please use the microphone. I think in that case, there's Zoom.
So I checked. So the guys on stream are not here repeating.
Okay, I try to repeat. Oh, sorry. Come here and then.
No, you can.
Okay, I will repeat it. Okay.
Yes, I was wondering if there are any theoretical limitation of the method for finding correspondences regarding the baseline of the camera pose in general. For points, the triangulation is like easier, but now that we are assuming that the data source that it's linear in their direction, if the cameras are too faded or something like that. That's any limitation with the gradient of the projection in the data to show that the mathematical part.
Oh, should I repeat it? Because I don't. Okay, but I am not sure that I understand very well. Yeah. So are there any theoretical? So are there any theoretical? First, I want to try to answer that. Okay, and then in that case, I try to summarize the question. Okay, because you mentioned that for the special cases, there are theoretical limitations. So there are theoretical limitations. Oh, okay. No, I understand the question. So are there any theoretical limitations for computing these geometrical entities like the camera pose? So yes, the answer is yes, because for example, I go back. in that slide I placed, the affine transformations can be retrieved. And the fundamental matrix itself can also be used because the fundamental matrix gives constraints for the normals. Okay, it gives the scale along the normal direction. Okay, and if these line directions, for example, are parallel, then numerically the problem becomes unstable. Okay, so in that case, so it's better if different directions are given in this example. However, for the camera pose problem, for example, we haven't found any limitations for the estimating the camera pose but when the surface normals were computed. So in that case, I remember problems because in urban environment there are horizontal planes like the road, or there are vertical planes like the walls of the buildings or the sides of a bus or buses or a truck. So sides of big vehicles, and in that case, unfortunately, if we use line directions in these walls, and they were parallel to the normal of the epipolar lines. There were cases. So in that case, an accurate reconstruction for the surface normals wasn't possible. And that's a pity because, for example, the surface normal for a vision system of an autonomous vehicle is very important. Okay, because if we take the surface normals of the road is perpendicular. So if we find oriented point clouds when the surface normal is vertical, then we believe that that's the part of the road. If the surface normal points to us, to the car, in that case, maybe it's a wall or it's a surface of another vehicle. So that's an obstacle which should be so the control is required to avoid the collision. Okay, so and this is why this is a problematic part. Camera is mounted on a car. In that case, the camera pose, the odometry, the movement of the camera can be accurately retrieved. But unfortunately, the surface normals for the walls weren't good because there were it's a limitation, because in that case the linear equations in order to estimate the surface normals was unstable mathematically, numerically. Do I answer your question? Thank you. Yes.
One more question. So there was example for driving, and say if the road is flat and so we want to find correspondence and we are happy, but what if the road is like going up or down? Like how we would actually make it like error or it would not?
Okay, so the question was that what's happening if so there were a video and in that case planar motion was assumed, and Dima asked what's happening if the road is not planar. And my answer is that in that case, the algorithm fails because it assumes that the road is planar. But unfortunately, we haven't tried that case. This is why I think it's a very good idea to involve the gravity directions into the problem, because you know that so if you know the gravity directions, in that case the camera image can be corrected if the vertical direction is known, because by a homography you can correct the image, and in that case only that assumption is not true, that the movement is on the road, because in that case there is movement along the vertical direction. So in that case, one additional parameter should be added to the problem. However, as one affine correspondence gives three equations, okay, in that case the movement, the translation is translation consists of two parameters, and as it is an arbitrary three-dimensional direction, and but the rotation is along the vertical direction, because from the IMU the vertical direction can be corrected. Okay, but this was a very good question. Other remarks or questions? Yes, please.
Okay, so for the transit, the hardness norm paper in the just review things and on reasons from.
Oh, I don't understand the question. So the hard list, there was a question about the triangulation. Sorry.
So I wanted to ask, are you thinking of like preview triangulation or some number of views there too?
Yeah, so the question was, do I know free view triangulation? Oh, unfortunately, I don't know, but this doesn't mean that there aren't any free view triangulation correction algorithm. Do you know? Maybe the audience knows. I know that my colleagues extended the two-view correction problem for the affine transformation into a multiple view problem. But in that case, ask Daniel, because he's the co-author of that work. You published it in BMVC 2019, maybe.
Yes, of course, you can do the triangulation from multiple views, but it's not even accurate from one view, because in that case, the flat transformation is not strong in the depth. Basically, it's stronger rotation and such things. So it doesn't have much when estimating the depth of the point. Of course, you can extend it to having like n images, and you use all the Affine constraints from them, but they don't necessarily in the current form.
Yes.
Because they are noisy and they are not very strong in the depth. They are stronger in the direction of the ray.
Yes, and for the free view problem, the trifocal tensor can be applied. But to be honest, I don't know anything about the trifocal tensor. Only I know that it exists, and then I don't know any triangulation algorithm for the using the trifocal tensor.
Sure. And so in your simulation for big Affine correspondences, you imagine a cost function that depends not only on coordinates, but also
Maybe. Okay, other questions? Okay, so in that case, this part of the tutorial is concluded. Thank you for your attention and thank you for the good questions and remarks.
Hi. So, okay. Okay. So my name is Dmitro, and I will tell you how to find this affine correspondence, which Levent and then Daniel, and also Jimmy will like tell you how to use. But like you need to have them right to use, and that's the thing. And yes. Yes, so the slides are available on our website. It might be not the super latest version, but the difference would be like minimal. And so if you would like to like go and check slides, so you go there. Okay. So let's first do some kind of like what are the correspondences and what do we mean? Like let's be the first, like formulate the thing. So we have some image. And it's consists of some observations. And like by observation, I'm really general. It can be patch, it can be pixel. And this observation consists of two parts. One is spatial information. And for a pixel, it's like just coordinates of the pixel, X, Y. And the descriptor, and here for pixel, it would be RGB. Or it can be like, I don't know, event camera, where pixel would be again coordinates and timestamp, and then like, and descriptor would be like this gradient change. Or it can be region, and the descriptor would be like a sieve descriptor or some like superpoint descriptor, and then so on. And the spatial info can be also like our affine feature, which gives us like oriented ellipse. So that's like pretty general. And all these observations also have in common that they were obtained under some conditions by some sensor. And we have this sensor information. It can be known and unknown things like camera pose, illumination, sensor type, and so on. And we have another thing, which is like another image which is taken by another sensor, maybe in another time condition, and so on. It also consists of different observations, and the correspondence is a link between them, like saying that it is going to like the same 3D or 4D point, and 4D means like in time. And the correspondences must satisfy some kind of world model. And here, as in stereo vision, the world model would be represented as a people geometry like fundamental or essential metrics. And their error would be like some smaller than something. And we would be interested in a local geometric correspondence, which means we have some scene which might have like some temporal changes, like building change, but it's like some scene it is like in real world or in simulation, and not something semantic like eyes are corresponding to other eyes and like these kind of things, because then the actually world model would not apply at all. So we need this local geometric correspondence. And so we probably all know that, but just like little motivation, why we need correspondences, why we need like affine features. They like correspondences are workhorses for basically anything which is related to 3D reconstruction, like 3D reconstruction per se, like in COMAP, or for SLAM, if you like you do camera, or for visual localization. And also right now you can do this with like different deep learning models, but often like I really love this paper saying that, okay, you can have great results just with visual localization with from essential matrices. Basically you detect features, like you do localization from relative pose, and it's fast, it's efficient, and it's precise. So this is like, it's like quite old concept, but it is like still used nowadays. And here is a common local feature extraction and description pipeline that you have like two images. First, you detect some features there. The features can be different. Here they're shown like affine features, which are oriented ellipses. You take some measurement region, the thing which you use to get your descriptor. Even if you think you don't do this measurement region selection, for example, you are using the super point local features, or you are using disk local features, they don't do anything about the measurement region selection. You still have them, even they are implicit in forms of receptive field of the CNNs. So it's important to remember, even if you don't see something, it doesn't mean that it does not exist. It exists, you probably just don't know it. Then we do like this kind of descriptor, like sift, hardnet, then do matching and filtering, and then you find geometry from these correspondence. So I would be focusing on this two part, like detectors and measurement region selection. And other thing, like I assume for this talk as a like known and black box and so on. Things do not really change. If we do dense correspondence, they do a little. For example, here is how you do optical flow, and the optical flow is also correspondence, the point correspondence computed densely. However, nothing prevents you to apply the same techniques, which I would be sharing about, like getting scale, orientation, and like some affine information, actually also densely. So the things which I will be explaining, they are not just tied to this classical sparse local feature pipeline. They are completely applied to the dense things. And there are also papers called like dense flow, affine flow. They are like older papers. There are also modern papers which use affine semantic correspondences, for example, to do the like matching of different types of cars. And there are like I'll cover the different types of local features, their covariance, and like you already see in the slide. And there are like many families of local features, like classical, Harris has seen. Superpoint, they are just translation covariant, which means like you shift your image, but they also your key point coordinates are also shifted, like nothing changes. Like more other features like shift or orb, they are translation, scale, and rotation covariant, and they often output these parameters like estimated, which means that if you detect like something on this image under and your like translation, rotation, and scale covariant, it would also detect roughly the same area in 3D space, or more precise, how this 3D space is projected to the 2D. And because 2D is 2D, like it's an approximation, but like more or less like this. And you can also have something affine covariant, which doesn't give you like full perspective covariant detection, but it's like as close as possible to it. So okay, and I'll cover all these different types of local features and what how can you do it. So let's think step by step. I don't know if you're following these GPT-3 things and zero shot learning, but apparently if you add this magic incantation, all the answers these language models give you become better. So let's try if it helps human as well. So we would like to have key point locations, and this is like necessary to have point correspondences in Affine. And the algorithm is actually, regardless if it's deep learned features or classical, it's like pretty simple and like the same. First, we compute response map. Response map means that you have some function which per each pixel gives you output is safe, is it's a good local feature or not. Then we find local maxima here, like if it's like the best in the neighborhood, and then filter responses like by different ways, either by threshold and by some threshold, or just take in top K features. So let's see how it works. So I took one classical local feature like Hessian response. It's like was linear filter, and Superpoint and Kinet, like they are both deep learned approaches. And this is how unfiltered response map look like. And actually, you can see that many of the things, like some image locations are good for all of these things. Then we apply non-maximum suppression, which means we remove everything which is like not maximum in their neighborhood. So, and we can display them here as key points. That's what's usually they're taught at computer vision courses. That's what people use in practice. We have key points. Like this is kind of synonym for local feature, and that is like not very true. But that's kind of the common assumption I'm going to work with. One. Clarification about non-maximum suppression. If you Google for non-maximum suppression, they're like most outputs are for this for object detection. And in principle, this is a quite similar thing that we have several kind of candidates for something. In object detection, it is objects. Here be car, of course. And you would like to find which this bounding box represents the how horse or car is the best. For local features, it's very similar. That we have like different candidates for local feature location, and we are sure that they are actually the same local feature, and we would like to find the best. And in object detection, it's done usually by comparing intersection of intersection or union overlap, and then we get it like the best thing. Whereas for the non-maximum suppression in local features, it's much more simple. Like you're just apply like if X is equal to result of max pooling over the here, then it's good, otherwise it's bad. So this is like pretty, as shown here, is pretty primitive, but that's based on our assumptions. And because this was actually developed for very simple local features, it may be, and it would be good if someone would explore some more advanced methods, like go from object detection NMS to local feature NMS. But like that was kind of subtle. So okay, we have key points. But remember that, as I told you, each CNN or filter, for example, for difference of Gaussian or Hessian or Harris has a receptive field. Therefore, we have a scale, even if it's not precise. So when you have a key point, it's never a key point. So it's actually, you have this X, Y, and scale. And here, as you can see, all circles in each image are the same. So that's because like I detected on just one image, I applied like Hessian filter or super point or Kinet, and they have like all the same like scale associated. So this is good. So we know which part of image we have like associated our key point and descriptor. But that is not scale covariance, which means if you zoom out, for example, and run the same detection, you might get the say like translation covariant key point locations, but the detected scale, because it's constant, would be different. That's not good. So we would like to go from constant scale to some kind of scale selection. For linear filters and classical handcrafted local features, that's rather simple. The image processing math comes to help us, and it says that it's the same if you actually can have your filter non-changed, but you can apply this on the Gaussian blurred image, and the bigger the blur is, the actually it would correspond to like bigger feature you would be detecting. And here we are applying. So we have these different like blobs. Basically, we have point, and then we around each we do Gaussian blurring with different sigma. And then we run our Hessian or DOG, which is DOG is like detector and sift. And show this like response. And you can see they have a very nice peaks, which means that we can do also non-maximal suppression over the scale parameter, and then we'll have our scale. And that's how handcrafted scale covariant detectors like Harris Laplace, SIFT, Hessian Laplace, and Hessian work. That basically we run them on a scale, on Gaussian pyramid, and do like non-maximal suppression in not 2D but in 3D. You can also do something which is even more clever, because the filters are linear. You actually can find the subpixel localization for both scale and key point location when you feed quadratic into your signal, and then find the extrema, so local maximum or local minima there, which is like more precise than your pixel grid and then your scale grid. And that's why the like SIFT detector is so precisely localized. If you check, for example, different benchmarks, for example, for homography estimation, for like especially for homography estimation, and there are often graph that Y is like some accuracy of estimation, and the X is you vary the threshold, what is like correct key point. And whereas in the like some loose threshold, deep learning methods are great. In the very beginning, when you would like 1 pixel or less than 1 pixel accuracy, is almost always sifted the best. And this is a like reason for this, because we have this part and we don't have this for deep learning. So okay, for Hessian detection, as you can see, we apply this procedure, and we have this nice different size local features. So that's nice. So what can we do for learn detections? And there are several strategies for handling this in local. So first is denial. And we say, no, we don't want to deal with this. No. We just output key point location, X and Y, and that's it. And this is actually works well for descriptor because you have descriptor baked into the local feature, like for superpoint. For disk, they have this implicit receptive field, and the descriptor is already calculated. You cannot use this math which Levent and Daniel talk you about, but you can use this for matching, and you can use your point correspondence. That's working quite well. The second strategy is anger. So, okay, tell me that I have only one problem, and I do a not Gaussian, by scale pyramid. I downscale my image like by factor of 2 or square root of 2 or different, and I keep key points from all levels. That's example for ORP or Kinet or R2D2 for multi-scale. They are doing this. So, and that works, but there are like two problems associated with this. First, as you can see, you have many like duplicate detections, which is also might be the case, for example, for Harris corners, but there are some other like classical local features, but here it's exaggerated because we don't have this scale non-maximal suppression, that we have like feature for every scale. And the second thing is that your scale estimation only as precise, like your scale covariance, as precise as dense your scaling strategy. Like if it's a factor of 2, as in, or for example, you would have either 32 scale associated or 64 on 128, so on. So like it's very noisy geometrical data, but you have something. And third is acceptance. So okay, so I need to do something. What can I do? And one possible answer is to train separate scale estimator per each key point location, even for example for superpoint. That's a paper which presented at this CVPR. I have nothing in common with this paper except I found it. I actually pretty like it. It would be presented on 24 on poster session. So if you're interested, let's go, and I will cover it a bit later. So, and because we need local affine features, so we part our ways with superpoint for now. But if someone would train new version of superpoint, which also outputs scale, orientation, and maybe a fine shape, then it would be cool, because superpoint is like super robust. It's very good local feature. The CVPR paper, train a fine superpoint. Okay, we have Hessian, we have Kinet, like classical and learned. So then we can go to the orientation. And again, as with the scale, we have some orientation already. If we don't do anything, we assume up is up or gravity prior. So all our features are oriented like this. And the thing is, like, if you can rely on the photographer to do this kind of orientation, that's actually a very good thing. And this is like huge table of numbers from our benchmark paper. What's interesting here is this delta improvement with this upright plus, and NI is number of layers, and MA is camera pose accuracy. And basically say, if you're sure if your images are upright, you just skip any orientation detection, you use this information, and you got improvement, because if you don't detect it, you cannot break it. For example, sometimes even the best orientation estimator failures, and the gravity of prior, if image is upright, it never fails. That's good. But if you cannot rely on photographer, or if you do need something precise, or you do with UAV and you actually have like no gravity prior, you're looking down, right? Then you detect some kind of canonical orientation. And there are multiple ways how you can do it. Classical approach is dominant gradient orientation, which is used in SIFT and other methods. So you extract scale normalized patch. You already have scale. You calculate image gradient per pixel, or like patch gradients per pixel. You convert them into polar representation from X and Y into like magnitude, radius, and direction. And you gather them in the single histogram, weighted histogram, weighted by this strength of the gradient. So here is like just 8 possible directions, and you take the maximum. And then like that's it. That's very simple, very efficient, and it works well. That's, for example, how it would work on a toy example. And this is how it would work on non-toy example. But here is like, this is non-toy, but also like huge gradient is presented where you have from left to right. What is important here is like this toy example, like the orientation estimation is perfect. So it's ideal for this case. Here we have kind of difference. We have this occlusion by this tree branch. And you can see that orientation estimation is not that repeatable. It's not a problem for descriptor, but it might be a problem if you would like to use this orientation information for your geometry estimation. So later, okay. So here, what we have is a summary. So we have our X, Y, and scales. Yeah. And by the way, this chart over the road from my work in Prague. There are like other approaches. Why I'm covering this, because so sometimes they're like very old ideas are very efficient and simple, and maybe you can revive them with deep learning if you want. So another estimation, if this works only for specific key points, which are corners for fast features in orb, and that in corner here you have basically like segment of one color, darker or lighter, and surrounded by others. So you have this sector. And you can estimate this center of the mass, and you then orientate it to be X or to be Y or whatever. So that's how orb local feature estimate their orientation. And this is quite precise. And there is even a name in Daniel's presentation, which he will share, the so-called like orb solvers, which assume X and Y and orientation, and no scale. Why no scale? If we have it, yes, but it's like super imprecise. It's 32, 64, it's like huge error. But orientation is good. Finally, you can train CNN to regress a repeatable patch orientation. And the best thing is that you can do this in completely unsupervised way. Or like in augmentation supervised. You don't know what is the best orientation and what is canonical orientation, and you don't need to. So you just feed the patches into CNN, and you construct your loss functions. Sorry, you get one patch. You can have two, but like you have one patch. You generate two synthetic rotations. This you feed into CNN, and you would require that these orientations should be consistent with each other. So when you project them, they would have like point to the same orientation with respect to the original patch. But you don't know what is this. This works pretty well, and it's actually better than this SIFT dominant gradient orientation estimation. There is funny thing about this. Whereas SIFT dominant gradient orientation estimation have some like meaning to us, like, okay, we understand what is this. Here it's just random. So because network doesn't care about meaning, it cares about repeatability. So as you can see, to do this slanted view, But the benefit of doing this over this classical and understandable thing, this actually, it's you have better repeatability on a real world patches with occlusions and so on. So it's if you have resources to run little CNN, so use it. It's better than doing like classical approach here. And they are actually quite like sometimes they are in agreement. Like if you draw, for example, as here on this clouds orientation, this orientation, sometimes they're like super different. But okay, that's it. So time for a little bit of advertisement. So the many slides and all these visualizations are created with help of Cornea library, which is like basically computer vision in PyTorch, which I maintain. That is the idea that right now nobody needs files. So many people still need to do C++ thing, but better to do it everything in Python and using your favorite PyTorch deep learning library. If you're from TensorFlow, sorry guys, and basically you still need to have classical approaches, like it can be geometry, it can be like this rig projection things for camera pose, it can be this orientation estimation, like so for all things which I showed, like almost all things, like here where this, yes, look why I cannot go. Okay, now I can. So this orientation estimation and so on, they implemented in Cornea. The visualization is also from Cornea Moon's company library. You have Hessian detector, Kinetics detector, very nice to work with. So shameless plug done. So now the thing with Orinet, it's problem that it tries to regress orientation. And sometimes it can be there are like two dominant orientations. Imagine you have just like literally a circle with two arrows drawn on it, like two identical arrows. If you do regression and you, for example, your method is trained to pick these arrows, you would get like some random estimation edges there or there, and sometimes it's not right. And this S3 estimation, it actually does this as a classification problem, which is quantize the scale and orientation and run a distribution and train in this way that although we don't know canonical scale, we don't know canonical orientation, we would like them to be covariant and in correspondence. So if like scale 21 is correspondent to scale 6 in one image correspond to scale 16 in second image, the next one here should correspond to next one there, and so on, so on. And this allows you to pick multiple orientation and multiple scales. For example, here is like 2 input patches. You do this estimation, and here are 2 picks for orientation and 2 picks for scale. This gives you one local feature, like one orientation per key point location in for one patch, and actually 4 possible patches in patch 2, which is bad from combinatorics, but good when you don't when you cannot allow to lose correspondences because you are too few. And then, as you can see, you have recovered this, and maybe you can apply this thing on top of your superpoint detection and local features, and actually get the upgrade from superpoint to rotation and scale, and then use superpoint with this thing in order to estimate this affine geometry which Leventa talked about. Okay, so right now we have X, Y, scale, and orientation, 4 parameters. We are not yet done. We need also a affine shape, which is shape of the ellipse. So we go from circle to ellipse, and it has like two parameters, which is a direction of the being more long, and actually how much your axis is longer than short axis. One of the like classical and like simple approaches is use second moment metrics of the image gradients. It is a super old idea. I think first one it was from Tony Lindenberg in '87. Actually, I thought that's just from Baumberg, but Jimmy proved me wrong. And it's also almost the same idea. It was used in Baumberg and then in Mikolajczyk and Schmidt paper for Hessian affine, Harris affine, the famous classical detectors. And the idea is very simple. First, we estimate a gradient. So like per patch as the same as we did for orientation. And then we construct this per each pixel. We have like second moment matrix, which is 2 by 2, but the non-main diagonal elements are equal. So we have 3 parameters. We just like multiply x by x, x, y, and y, y. We have 3 parameters per pixel. We integrate over all the patch, and we have our ellipse affine shape parameters. And what is nice about this second moment matrix is that it actually rotates the same way as you do with any affine change of the patch. So it allows you to normalize for affine shape. And it like just for a little example, it works like this. So there are pluses and minuses of using this. And by this, I mean like affine shape in general. One thing, or good thing, that you can use all this geometry estimation nice things. Second, if, for example, imagine you have kind of a weird designer house where some windows would be like this first one and second would be like second. Then like for standard detector like CIF, which is not a affine covariant, you would be able to distinguish between them because they would look different. But if you normalize, they would actually look the same. And always, if you get something in robustness, you often lose in discriminativity. And the same goes for scale and orientation estimation. And it also, not only because of possible failure of orientation estimation, we had a better results with just gravity prior, but also because we lose in the discriminativity of patches. That's like very important thing for practitioner to remember. Okay, that's like classical method. It is working well, but of course we can do something and to learn this. And then whereas for the affine course, for the orientation, it is like pretty clear how to create a loss function. For affine correspondence, it's not that way. So we would like to do it differently. So let's first just recall how we would like to learn local descriptor like shift replacement. So we have many pairs of images, and in these many pairs of images, we have some patches. And like let's assume 2-dimensional descriptor just for the visualization purposes. So we have these patches, and they match to descriptor space. Here, they are small a's. Okay. So this is we have from image 1. And then for the corresponding location, we have also patches from image 2. This is kind of a standard metric learning task. And what would it be like in that in descriptor space, that embeddings of our patch, like corresponding patches A1 and B1 would be as close as possible. Like ideally, the distance is 0. And then they should be far from non-matching patches, which is all others, right? So this is, you can formulate it like triplet laws or hinge laws over the all possible pairs or over the hard pairs. And that's how we actually train all the local feature descriptors. Like in more or less in this thing, you can do CMEs, you can do contrastive or triplet. Like all the descriptors are learned one of this way, like superpoint, hardnet, R2D2, so on. Like that's the same thing. But we also can use this laws and this idea to estimate a fine shape, especially when we actually don't have perfect ground truth relationship. Often, for example, for patch database or for ColMap or whatever, you have like point cloud correspondence. So you can have, you're sure that your some center of patch which you extract from image is correspond to another like a center of the patch which you extract from different image, which is going to the same 3D point. What you don't know is how is there a relationship, for example, between maybe orientation and affine estimation. So roughly it's okay, but like not fully registered. And that's how we deal with this problem. So we sample this in imperfect correspondences. And then we apply some random affine transform to them. Then we crop patch and we go into Affinity to estimate the affine shape. And then we use a spatial transformer, or basically PyTorch grid sample as it's implemented, which implements bilinear sampling in a differentiable way to warp our patch according to our estimated affine shape. Then we go through our descriptor. It can be SIFT, it can be hardnet, whatever. The main like thing that it needs to be differentiable, and if it's in PyTorch, it is differentiable. And then usually, and then you apply this hard negative loss. This is like basically standard or triplet margin loss. And so what does it mean? So we would like to find such a fine shape which benefit our matching. So which means that the matching becomes easier if you apply this. And there are basically two things. One thing is it would enforce in implicit way the repeatability. So these shapes are covariant. And second, there are many like different shapes. For example, it can be very circular, or it can be very elongated. And for example, very elongated shape, although like super repeatable, can give us distortion, and it makes our descriptor life easier, hard, sorry. And that's why this add additional constraints that we don't only care about repeatability, but also matchability. And there is a little trick about what to do with negative gradients. It doesn't really important here. And that's the way you optimize this. And this is how for our example, look like that our normalized, descriptors of our normalized patch with estimated affine shape, I actually go together and far from other. So the same color corresponds to the same location. What is important when you do deep learning with geometry task? It is that parameterization, it matters, and sometimes it's matter a lot. So here I would like to share some tricks. One is that if you just blindly parameterize a fine shape as 4 numbers, it's quite hard for network to learn. Instead, what you can do is first you decompose orientation as from orient and define shape. This already make things much easier for network to learn. And one more thing, which is I never recall any example where it would hurt but not improve. So this trick for ResNet. So if you have some prior, just learn the residual. So for example, for ResNet, you have identity matrix for features, and you learn some correction. Again, here we have some shape prior that circular shape is probably not the worst shape. So, and if you don't know anything to do, you have circular shape, and then you learn just residual correction to each shape, and it works. It's works the best. Okay, so how it would look like, and here I applied for the Affine, which is this second moment matrix approach in Afnet. And if you look here, they look very, very similar. If you look in detail, for example, actually it's pretty hard to find, but so this Affine is a little bit more elongated, but overall they actually work in very similar way. So, and probably it's because of like nature of the task, it defines what is repeatable shape or what is not. But let's go a little bit in more details. So we have some, I have some image where it is, there's name hotel or something like this. I work with it with random affine transformation, like 2 of them. And then I feed this into second moment matrix rectification. So this first row, and use this rectified like parameters to warp it back to canonical orientation, canonical shape. And then this is second row when I used second moment matrix for doing this, and third row when I use Affine rectification for doing this. So as you can see that they are similar, but left and right are more different for the handcrafted approach rather than learned approach. And that's kind of like, okay, that's reasonable, and Affine like looks like almost perfect. And here is again a problem why not everyone in the world is using affine correspondences, because it's, as Daniel said, it's simple, but it's not trivial. You need to know what to do. And here is example. So I told you that I used this to estimate affine transformation and then warp the patch. So here is kind of residual affine transformation from the between this estimated thing and original. And one thing, I don't need it to be identity, because maybe some canonical shape is not just the frontal parallel view. So it's okay that it is not identity. However, what is not okay is that this left matrix is not equal to the right matrix, which is this rectifying transformation like residual from this left patch and to left matrix and to the right patch, right matrix. And as you can see here, the second moment matrix rectification is more imprecise than Affine, but Affine, even the image looks almost perfect, and like I'm thinking that descriptor is pretty happy with this rectification. In geometry, as you can see, it's quite not. So there are quite significant differences, which make the affine these affine parameters noisy for geometry estimation, and that's why you need like special techniques and special care, which Daniel would cover. Okay, this is like 2 most common things. There are actually much more ways how you can get affine correspondences. Many of them are like forgot now, because why do you need them? But it's often happens that actually some paper in deep learning world is actually some using an idea from 80s or 90s and reapplying this. And I hope to kind of convince you to try to do something like this. Or maybe for your particular case, actually even these ancient features would work. So that's for intensity-based regions. And it's actually completely different approach than we have before. What we have before? Okay, actually, I forgot to slide subtitle. So we had, for example, in here, Hessian affine. So we have one way to detect scale and XY. Then we apply another method to detect orientation. Then we apply yet another method to get our affine shape. So this is like quite long procedure. And this is for response-based key point or local feature detectors. They are like pretty common, but there is another approach. And the another approach is to detect regions which are not have just X, Y, scale, blah, blah. No, they're like arbitrary shaped regions. And then if you need like affine parameters, you can do something about this later. And here is, for example, you take local intensity extreme, or you can also take like response extreme, and then you have some function which you apply along the race from this center to all directions, and then you save the numbers of this your function, and then you pick extrema, like maximum or maybe minimum, and then and that's defines where you stop along this rate. And you repeat this for all directions, and this gives your region. And if you construct this function f properly, that's like in a good way, which is like not random, then it would give you a repeatable region, and this region would be like having the same correspondence. And this, and it's you can use geometric moments of this function, or this sorry, not function, contour, to get the actually your affine shape. So like second order moments give you actually like covariance matrix, and this of the ellipse, and this is what you need to get a affine feature, but you actually have a whole contour. So that's one approach. Okay, that's just that is actually covariant with affine, but I think you probably believe me that it is. So, and there are many more detectors. Some of them I'm going to cover. One is MSR. It was very famous in the past, and it's actually was often used, for example, for letters detection and so on. And it's a very simple idea. So you treat your image as a grayscale image, as a kind of 3D elevation thing. And then you start to threshold on some level and see which contours you get. And the contours which not change when you change this threshold are stable regions, and you save them. And so say they are my regions. Okay, why didn't it work? Let's try if it works here. Okay, it works. So this is not 3D, but it's 2D visualization, and you can do this thing from two direction, going from light to dark, and from going to dark to light. That would gives your two kind of features, which is like basically dark blobs, but not as a just circle as in dog, but like really contours. The good thing about this approach that is very stable with respect to like your camera movement. Like if nothing moves except the camera, it's stable, especially if you have flat or relatively flat thing. And it's invariant to affine transformation or brightness or contrast change. And there is also like very efficient implementation with respect to number of pixels, basically of image size. So what you can do with this, then you have contour. You already know what to do, right? So you get you calculate this contour covariance matrix, and that gives your ellipse, right? That's one way. But there are other ways. This is what makes it interesting, is that when you have contour, there are basically almost infinite way, well, not really infinite, but like a lot of way how you can construct affine features on this, and actually not one, but multiple. For example, one thing covered in this paper, link below, stable affine frames on isotope photos, is that you can get a convex hull of your region and find the points which are actually touching it. So this would be this white guy, and then you have concavities, and on concavity you have the like deepest concavity. And if you take a triplet, one point of the boundary, second point of the boundary, and as a center you have this concavity point, that's 3 points. And as you already know that affine frame can be parameterized as 3 points. You have 3 points, so you have one affine frame, but you have more concavities, So from one region, you can have multiple local affine frames, which you can use for your computation, and also it for description and so on. And this was just one, like particularly good, but just one way how you can convert a contour to something which you can use to get a affine correspondence. I'm not going to go over the things, but the idea of this and the next slides is that there are multiple properties which you can use as, like, you can calculate center of gravity, you can use concavity, you can use like some farther point on the contour, so some closest point. You can have some combination of them, and you can construct your own affine frames from this. So that's very cool thing. And this also is quite precise. In fact, it is more precise than using this stuff for Affnet or Hessian Affine and so on, because these things on contour give you like pretty good constraints. They are not as noisy. But of course, there is a catch. These segmentation-based methods are much, well, maybe not that much, but like significantly less robust with respect to real 3D world occlusions and illumination change. For example, if you have SIFT, which is blob, and then you have, like, I don't know, 3 branch over this, you'll still detect this. It may be a little bit shifted, but you will still detect almost the same orientation, almost the same key point location, and so on. But if you do some contour based and you have the cut this contour, so you're doomed. You don't have the same contour anymore. And this is also shown, again, this is camera pose estimation with different local features with the same descriptors. And as you can see, this dog, which is like detector used in SIFT, is better and has an even better and has an Affnet and Affine. But the MSCR is here. It is not as stable because real world is not planar. However, maybe you can use stuff like how to say, like, again, maybe you can apply some deep learning based segmentation, which is much more stable than this simple intensity based segmentation. And from these contours, you can construct your affine frames, or you can actually, so we are speaking about affinity here, but in fact, you can construct on these contours things which are also covariant to perspective transformation. And you can estimate homography just from this perspective correspondence. That's huge power. Okay, let's go next. There is third family. So first is you can use this upgrade using like Affnet or something to get your affine shape. Second approach is use segmentation-based detector. This third approach, which is you can get your any local features used, and then you use test time augmentation to get your affine covariance. And the idea is simple. So you take your image, you apply some affine transformation, or it can be in perspective, but it's like more images to sample. And then you have these kind of images. Then you detect as usual, and then you reproject your, for example, similarity covariant features like circles back into your original image. And in original image, they become oriented ellipses. Here you go, your affine features. That's very good. Unfortunately, you need to do quite a lot of sampling to do this. For example, here it shows like this is like view sphere, and you sample 2 parameters. One is tilt, so how you got from pole to equator, and second is your longitude. I believe it's longitude. So this angle which you goes around this circle, and you do this in a way that, like, near pole you need to sample less densely, and near equator you need to sample more. densely, and then you do the thing, you detect, you project, and you have as a fine covariant as your sampling is dense. And for this kind of sampling, as Daniel told me, this actually even can be more precise with this just time augmentation approach than with Affine, for example. But of course, it's very costly because you need to run your detector and descriptor as many times as you have your this transformation. One important thing so is that you always should apply Gaussian blur in a direction of your this tilt. So here it would be like this, and like in the direction of the squishing. Otherwise, you would have huge aliasing, and it's really not good. Okay, there was like a shift was proposed in 2009, I think, and since then there are like improvements on this idea. One of them it was from 2 years ago from Toft and Carters, and they were using monocular depth estimation to make this thing like much more efficient than in A-shift. They say, okay, you have monocular depth CNN. Then from the depth, you can get some estimation on surface normals. They would be noisy, but they're okay, good. And then you can use this to get two things. One is segmentation, this green, yellow, and red thing. So for those which are like similar in planes, so you know these regions are on the same plane, more or less. And then you also can use the surface normals to estimate the rectification transformation to make this plane a frontal parallel one. And this means that, for example, what you need to do is actually to do 3 or 4 rectification. One of them is like 0 rectification, just using original image, and detecting there and reprojection. And it really improves matching when you have huge viewpoint change. For example, you are near like wall of the building like this, and from like other direction, it's really work well. A student of mine is like was working on this approach and make it like a little bit more efficient, and also draw this nice visualization. His name is Vaslav Avram. And so what he proposed, he said, okay, so one thing what we can do is use Affine and run this densely instead of running this deep CNN to get your monocular depth estimation. And that would give per point affine rectification information. Then you cluster these to get your affine rectification. And second, you can use several, like you can also cluster like per plane, per segmentation. You can find like several rectifying transformation predicted by Affine. Apply this. So this is like multiple greens, multiple reds, and multiple yellows, and detect there and reproject. The question is why it's better. There is an original approach, for example, with monodepth is better than I-shift in the sense that you don't need this like hundreds of sampling, you need only 4. And you also do it per region, not per whole image. Again, it makes its computation easier. However, it's used homography for rectification. And if you have like huge perspective change, it can result in like very huge images because of these perspective warps are very warped, and they are also like huge, like 20 megapixels from 1 megapixel image, because like this perspective change can be really severe. Whereas if you do affine rectification, it's much more efficient and computationally cheaper to do multiple affine rectification, and instead of one this perspective thing. And this is what works the best. Finally, that's not all the ways how you can get your affine correspondences. There's a fourth way, efforts, we just say that you have already point correspondences from the SIFT or from ORP or from whatever. And so we visualize this. So we have like few correspondences here, and here there are patches which corresponds to them. And you can see they are roughly registered, but there is quite a lot of distortion. So they're like not perfectly registered. So what we can do, if we already have our like matches, we can just use some kind of methods. We can do something optimization based, or we can just train CNN to take these two patches into account and output their like rectifying transformation. That's by Mariana Rodriguez. It was published, I think, 2 years ago, and called Locate local something affine something estimator. And as you can see here, that this locate rectification is almost the same as a ground truth. Which means that like we warp one image, save it into red channel, green channel, another into blue. So it should not have this like colored blobs, and this works really well. So if you have some rough correspondence and you need to use this for some geometric task, what you can do before using it, you can just first upgrade this and make more precise with, for example, this method, and then use it for your geometry estimation. Another way, it was also from 2 years ago. What you can do, so this network estimates your like perspective warp or affine warp. Basically, you have this geometrical parameter or something. Instead of, you can say, okay, I have a patch which is in some correspondence. I can split in some subpatches, like 9 subpatches or 4 subpatches, and try to register their centers. This is done is this multi-view optimization by Duthmanu, Schoenberg, and Polyface. And they were actually using this for making point correspondence more precise. And they show that if you have a robust but super imprecise feature like D2net, this can almost get precision, precise localization of the SIFT features and so on. So this like really powerful technique. However, they use in only for point correspondence. However, if you have at least 3 points, you can always recover a fine correspondence from them. And if you can 4, you can have perspective correspondence. And if you have 9, well, you can have more precise perspective correspondence. So that's another thing. So let's summarize my talk. If you would like to get just one thing from this talk, I would like you to remember that point correspondence is never just a point correspondence in practice. It's much richer than this. And there are many good methods to get a fine correspondence and use them. And third thing, a little game shameless plug. I now work at Hover, who does like 3D reconstruction from very little number of images. And if you're interested in this workshop, you know something, it's a very high chance that you would be interested in problems we have, and if you would like to work with me, so reach me out and so on. So what we do is allow people to take these several photos and then do measurements and so on. And you can say this is like kind of ill-posed problems, because you cannot have metric reconstruction from a camera without a scale, but there are ways how to go around. That's why it makes it challenging and interesting. Feel free to like reach me on Twitter. If you need to do like with something with affine correspondence, I would help to share code I have or whatever else, or just chat. Okay, that's it. Questions?
related to all of this, so this idea that the point corresponds to the for a while using for scaling information, right? And but there is still some kind of locality, right? So there's like this is like a trade-off between the local region and the global region. So it's a matter of the set of two currently. Because what you are describing is basically a and if you take it further, like that an entire you can speak of a distribution over the entire that gives you all these defined regions into something. So I was curious about the sweet spot where to stop things, right? So we can describe the point of where perspective transformation, but other properties of and you can also, because there is a region, you can always say that any point that is close to a key point also has a likelihood of being a key point and shares some of these components. So, where do you draw the line between, making things very local and describing very few parameters versus making them super global and describing the very high dimension?
Okay, I'll repeat question to check if I understand correctly. So the question is, where is the sweet spot because between local few parameter as like a representation of local geometry and some global geometry, like which is for whole scene? And the answer is, well, there is already sweet spot in a detector in the descriptor in that sense. First, like if it works for descriptor, for patch descriptor, it usually means that the locality assumption is good enough. Otherwise, it would not match or would not redetect. That's one thing. And second thing is, I believe that it's actually, they should exist both because local things are easier to estimate. And that's why we're estimating them first. And then we go to the global, which are harder to estimate, but we use like help from the many local estimations. And actually, I believe in a current pipeline, and maybe if you do something inside of NERF, which is do something like this, it also should work, but I haven't yet tried.
So, but it's just I'm curious where you where do you stop? I mean, why don't you use perspective parameters, and then why don't you use initial uncertainty? Why don't you use all these other parameters related to everything? For example, it's mainly derivatives and so on.
Yes, great question. So why do you use Affine perspective, and why don't we use uncertainties? And okay, for perspective, it's actually there is mathematical answer. Is that if you are very local, the affinity is a first order approximation, and you could not actually reliably recover the perspective from affine things. So this is because they would be indistinguishable, and that's then not enough constraints. That's one thing. Regarding uncertainties, the answer is actually because we are stupid and lazy. Because there are ways, and I think like I posted on Twitter months ago some method which actually specifically uses uncertainties in local feature estimation to get the uncertainty for epipolar geometry. They formulated it and in use. Why we don't use? Because we haven't think about this, because it's more work. But I think it's a very good thing and it should be used. And I like that such work come. Sure.
Second thing I think is that you mentioned, I mean, this is nice by the way, there are different parameterizations of different transformation. And that is the correct parameterization is quite important. Actually, in 3D, people have been suffering from this problem, for many years by now. And they keep treating rotations in many different ways, for example. And they there's a similar analysis for the type of transformation that you are interested in, say, right? And one type of other representation are useful in Twitter. For instance, Kinetics predict if and projected onto the Affine manifold, would then be in a computer set, it would then be a good representation. And the third thing is on.
Okay. The question is about like parameterization of like affinity and so on. Okay, so then I cannot give like a full informed answer. I can just share my experience. One thing, if you are dealing with homography, it's like the best way is to parameterize is as a 4 points and 4 points. Otherwise, like you would have like huge sensitivity in these two bottom parameters, and it will kill you. That's one thing. Regarding the rotations, like unlike 3D, we don't have this horoscope log problem, and actually like sine cosine will like unscaled or prediction and like throwaway scale, just two numbers, get a ton, works always well for me. And for affine parameterization, okay, this thing works for me, but I would not say this is probably the overall best. I haven't did like more thing, but it is that for more precise estimation, I think pointwise is better. For like general things, this is, but it also like again from my experience for AFNet and like registration, the most important thing is not only this parameterization, but the ability of network to basically use this like to register. Like one thing is, unlike for rotation estimation, which we can just regress the like just rotation and give your, for example, Euclidean laws or angle, and that's it, and it would work to train ORINET. For AFNet, for example, here, like if you know the ground truth relationship, you can say, okay, you can just have like Euclidean laws or some other laws on the parameters, and it doesn't work. What works is actually allowing the network to visualize in terms of like, you have to imagine you minimize the registration and like via descriptor thing. And the same I get when I was working with navigation for environment. Like if you train some agent to go from here to here, it is much easier to agent to actually to visualize some, I don't know, blob there. It tries to register rather than, okay, this is X, Y, please do. It would work, but this visualization is just much better. Yeah, one more question.
So I find very interesting case in our slides. It's about two pictures of the same object, but in a different light condition. Yeah. Such two pictures are in a different light condition, so I would like to know whether with such pieces, and how does the components look like? Because we know these two pictures look quite different. And recently I'm trying to solve that problem, but it's hard to solve.
Yes. Okay, so the question how it like AFNet and this method work with this huge temporal and illumination and viewpoint baseline, right?
Yeah.
Okay. So again, shameless plug. So this is from my super small but super hard benchmark called WX benchmark. You can find this on internet and so on. And I published in 2015. And in 2015, the MOS method failed completely. I recently re-evaluated modern methods like Lofter and Disk and all this kind of. They are much better, but for this image and like some other, they still fail miserably. So this is like huge, like open problem how you can work with multiple baselines like illumination, geometric, and so on. There is, I think, no huge data set. There is Affine day night, maybe something else, but like for training. And probably you need to do some rendering or approach or like to train something. But overall, yeah. So that's huge problem. Nothing worse there.
Okay, thank you. My second question is, I think it has to do with the speed of the, yeah, because let's say if I would like to, I will replace the or with the Affine and something about others and all that. But will the Affine work in the real time to satisfy the same tasks such as maybe something like that?
Okay. Question is, would Affine work in real time? Answer is no. Yes, that's first answer. Longer answer is if you have GPU available, then superpoint, like one stage, and if you train, for example, like super affine point, then it would probably work, but it needs GPU to do in real time. Anything which is needs some kind of rewarping or whatever would not. And the only thing which can beat orb slam in like orb in terms of speed is actually, I think, pop shift on GPU. Like if you are resource constrained, okay, very bad luck.
Okay, thank you. Thank you so much.
Other questions? Okay, any questions from Zoom? Then no questions from Zoom. Yeah, no questions from Zoom. Last chance, and if you don't have any question, then we can all go for lunch.